Bismillahirrahmanirrahim. Hi, have you ever seen one of those tutorials which teach you how to draw a tree? They draw a few lines, you're following along happily, and then bam, they tell you to fill in all the details, and you're left completely confused as to how to proceed. What does fill in the details mean? How do I go from this to this? I feel like that's what most programming courses do as well. They teach you the basics of a language, if, while, for, working with files, and you understand all the concepts. You're confident with them. But then you see other people's code and you look at expert programmers and you have no idea how to go from where you are right now to where these experts are. This is where this course comes in. In this course, we are going to discuss how you can go from basics to a level that helps you understand and write real-world code. What are the tools and tricks used by expert programmers? In short, through very simple methods, we will get a better feel of how to go beyond basic programming, and we take Python as our primary language. A brief note about me, I'm Dr. Noman and I have more than 15 years of programming as well as teaching experience. I have worked on many different languages and tools over the years. Until recently, my paid courses, all on different topics, were either bestsellers or highest rated. That shows you the wide spectrum of knowledge that I bring to this course. For the prerequisites of this course, I assume you have a basic understanding of the Python language, if, else, while, and for, basics of lists and dictionaries, functions, and simple file handling. We will cover some important aspects of programming. We start with some tools that are used by every programmer regardless of the language they use. Stuff that is essential to all code but hardly ever covered in beginner level courses. We then discuss some important time-saving features of the Python programming language such as generators, decorators, high-level functions, context managers, and functional programming. All of these are used heavily in modern programming practice and many people just have to learn them through years of experience. The next part of this course is going to discuss parallel programming, multithreading and synchronization issues, another very important concept you must understand to code in a production environment. We discuss these through a case study to explain why you need them as well as how to use them. Closely related to this, a highly important concept in today's programming practice is the idea of asynchronous programming. Python and JavaScript, two of the most influential languages in today's development, are heavily focused on this new paradigm. And we will cover this in a very intuitive, very easy to understand manner. Remember, the most important reason you're paying for a course is support. So please ask questions in the Q&A forum if you ever get stuck. I have a maximum response time of around 15 hours. Please use this to your advantage. Ask questions and you should be able to breeze through this course and go beyond a basic level of programming to the next level where your code will take less time to write, will be much cleaner and much easier to maintain. And since this course comes with a no questions asked 30-day money-back guarantee, you've got nothing to lose. So enroll now and I'll see you on the inside. Hi, welcome to the course and thanks for joining. Before we get started with the actual contents of the course, we want to make sure that we're all on the same page about the environment. Since this is an intermediate course, I expect that you've already worked with Python a little bit, but I highly recommend that you use the Anaconda distribution instead of the official python.org distribution. So if you already have python.org installed, that's fine. But I do recommend that you go ahead and download the Anaconda distribution. It will save you a lot of headaches because it has a lot of packages pre-built and it's a lot more stable than having to work with the base python.org distribution. So Anaconda is available for Windows, Mac, and Linux, and you can go ahead and install it for whichever platform you're comfortable with. One thing to note though is that you need to install Python 3.6 version for this course. If you already have Python 2.7 version installed, please go ahead and install Python 3.6 as well, because Python 2.7 is at the end of its life anyway, and you want to start working with Python 3.6 as much as you can. So anyway, go ahead and install Anaconda for Windows, Mac, or Linux, whichever operating system you're on. Just make sure you are using Python 3.6. Now the way to learn Python is really through what is called the Jupyter notebook. We'll see what that is in a minute, but here's how you start it. If you're on Windows, go ahead and start the Anaconda prompt, not the command prompt, not the Anaconda navigator, the Anaconda prompt. Once the Anaconda prompt starts, you can go ahead and run the command Jupyter notebook. Notice that we are in the home directory for the current user. My current user is Noman, so we are in c:users Noman, and we issue the command Jupyter notebook over here. Hit enter and it's going to open up a browser window for you. And this is going to be essentially the directory that you are currently in. So our current home directory is going to be listed over here. So this is your current directory and all the folders in that directory are listed over here. This is just your normal file system. So you can go ahead and look at the normal file system over here. So 3D objects, contacts, desktop, all of them are over here. So treat this just as your normal file system. You can click on one of these folders to navigate. For instance, if you click on documents, you go to home folder / documents, and you can click on other folders to navigate as well. If you're already familiar with Jupyter Notebook, you can skip the rest of this video, but I'm going to put a very brief introduction about Jupyter Notebook over here for the sake of completeness, just in case you have not seen Jupyter Notebook before. If you are on Mac or Linux, you can simply open up the terminal and type the command Jupyter Notebook, hit enter, and you will get the same browser window as you would on a Windows machine. So beyond this point, it doesn't matter which operating system you're on, they're all going to act the same. To set up the files that we'll be using in this course, you need to download the notebooks archive that is available in the resources section and then unzip it. So once you unzip it, you will get this notebooks folder out of it, and you can put it in your downloads folder, your documents folder, wherever you want, and then navigate to this folder from your Jupyter Notebook. Once there, you can click on notebooks and you will see all the folders that we are going to be using in this course. Since this is an intermediate course, I expect that you already have some familiarity with the basics of Python. But just for the sake of ease, I've put in some notebooks in 00-Python basics, and these notebooks can be used to review the basics of Python. So they include stuff like library functions, basics of functions, compound statements, loops, sequences, dictionaries, file handling. So all of them are there. If you want to create a new notebook, you can simply go to new and click on Python 3 and you will get a new notebook. I'm going to use this 01 getting started notebook to explain the basic functionality of the Jupyter Notebook. So if you click on that, you get this notebook out of it. The way the Jupyter Notebook works is you have these cells. So this green thing highlighted over here is a cell, and it shows you the inputs. You can input any valid Python code over here, hold shift, hit enter, and it's going to execute the code for you and show you the output in this output pane over here. So you can put in any Python code you want, hold shift, hit enter, and it's going to execute it for you. You can go ahead and navigate to different cells, execute them in any order you want. So that's the basic of Jupyter Notebook. It's an extremely essential tool if you're trying to learn Python, or if you're experimenting with some data or anything that requires experimentation and going back and forth between your code. So a lot of the times when you're learning Python, when you're learning a new tool, you want to go with Jupyter Notebook unless you have a good reason not to use it. In this course, we'll only be writing Python code in a basic script file in just the initial 2 sections. After that, we'll be using Jupyter Notebook to learn everything. So enough of that, let's get started. All right, so let's start with something really simple but really useful. It's one of those things that no production level software will work without. Almost all the software that you have been working with use this technique, but at the same time, hardly any course covers this topic. So we're going to cover this as our first case study of advanced programming, and hopefully you would be able to use it in your own production software, and it's going to make your life really easy. Now this will give you an idea of what's to come in the rest of the course. So this isn't going to be about programming per se. We're not going to cover any new construct, but it's going to be a tool that's going to make your life much more easy in terms of how you can debug your program, how you can find out what's going wrong, how you can find out what others' programs are doing. So all of these things are going to come in handy when you are trying to move from the beginner level to an intermediate or advanced level. So let's start with this example. So we have this piece of code over here. As the name suggests, it calculates the square root, but we're not sure how it's doing that. So imagine that you've downloaded a piece of software from the internet, or somebody gave it to you, or you got to a new job and you have this software that you have to work with, but you're not really sure how it's working. So a programmer's job involves just as much reading code as it does writing code. In fact, most of the times you have to read code and you have to do very little of the writing of the code. So you need to understand how code works. So we have this square root function over here, and it calculates the square root somehow. We're not sure how. So we're given this code, and how do we go about understanding this? So let's say we go over here and we run it first, right? So python 01-logging.py. So we run that and it calculates the square root of 36, right? So print square root of 36. The square root of 36 is calculated up to some precision. Fine. But how do we figure out how this code is working? So if you are a beginner level programmer, what you would do is probably you would go ahead and insert some print statements over here. For instance, in this square root function, we're going to put finding square root of x starting with the guess. right? So we're given these two arguments and we're going to print them out to see how our program progresses. So let's go ahead and put in some print statements. So we have some of these print statements over here. We're uncommenting these so that we can see how the program progresses. So essentially we're trying to output the different variable values, right? So let's go ahead and run this again. So, all right. So it says finding the square root of 36, starting with guess 1, and then it's checking whether 1 is a good enough guess. Well, apparently it's not. So it improves the guess to 18.5 and then checks again, and then it keeps going, right? So let's imagine that after taking a look at everything that's going on, I now understand how this algorithm is working. So just as an aside, the way it's doing it is it checks whether the current guess is good enough. If it's not, it improves it somehow. And if you're not sure how, this is the Newton's method for improving a guess. I'll post a link to an article that shows you how this works. But anyway, that's not the point of this video. The point is that you have these print statements over here and now you understand the code. But now what you have to do is you have to go back again and remove all these print statements, because you don't want to release your code to the end user in which it's outputting all of this stuff, right? We don't want that, because this is a lot of information and the user doesn't need to see all of it. All the user needs to see is this last line of output. So now I have to go back and uncomment all of this. So imagine that this was a 10 to 15 file piece of code, and now I have to go ahead and put them all back the way they were. In the future, if I have to take a look at the code again and see how it's progressing, maybe there was a bug and some specific value was not being calculated correctly, I have to go back and put the print statements back in and then remove them back out. This gets a lot more problematic, especially when you consider the fact that this code is released to a server and you can't change them readily, right? So this is a very real problem in the real world. So the way we're going to solve this is that we are going to use what is called logging. And that's the focus of this particular video. So what we're going to do is we're going to go ahead to another file. This is 01-logging-b.py. And here we're going to take the same idea, but instead of trying to print the values, we're going to use what is called logging. So this logging package is going to allow us to do essentially the same thing, right? So we have inserted logging.error, logging.info, logging.debug, and some other stuff over here as well. So all the places where we had print statements, we are now putting logging statements, right? And this logging you can simply import by doing import logging, and then we are going to do some configuration. But before that, you need to realize that this isn't specific to Python. Any respectable programming language is going to allow you to have a logging mechanism. So you can, for instance, in Java, you can search for logging Java and you'll either have simple log4j, or you will have log4j, and essentially you can use this logging mechanism in whichever language you're working with. So anyway, here the way we work with this is we import logging and then we set the basic configuration to log level debug. Now in logging you have multiple debug levels. Let's skip that for now, and we are going to come back to this after we have run this piece of code. So let's go ahead and clear this and run python 01-logging-b.py. So that's our log file. So essentially it's the same idea. The difference is that now it's showing the log level as well. So info, debug, debug, info, and everything is over here, right? So, but the problem is still there. We have all of this logging stuff in there. How do I get rid of this, right? So the way I get rid of this is I go ahead and change just this one line. So I'm going to change this line to, instead of logging.debug, I'm going to say, just show me stuff that has the error level. So we have multiple errors. The error level, so let's start off from over here. So the error level shows only that stuff which is extremely critical, stuff that is leading to errors. Then you have warn, which may lead to errors, but it's not a particularly concerning problem at the moment. Then you have info, and then you have debug. For instance, here we have just one error when you try to calculate the square root, which is of less than 0. So we can calculate that. So we have a logging.error, and then we raise a value error exception. So we have this error over here, and this is info. Info is essentially, that's what I'm thinking. So the program is going to output everything that it's kind of thinking, right? So this might be useful when you're trying to debug a problem that's difficult. And then we have debug. So this debug is extremely verbose. It's going to output everything. It's like the thinking aloud of the machine. So let's go ahead and change this to error. and then run this again. So notice that I've changed just this line from debug to error. And now I run it again, and as you can see, all the statements have disappeared even though they are still over here. And the reason is that if I set the level to error, it's only going to output stuff that is error level or higher. So there is no higher level, so just error. If I set it to warn, so if I set this to warn, it's going to output stuff which is warn and error. So if I set this to debug, it's going to output everything, right? So let's run this again. So here you go. Everything is output. Let's say I set this to info, and now only the info stuff is output, right? So a lot less verbose. So it depends on what you're trying to do. If you're trying to debug a problem which is extremely complicated and you have no idea, you can set the log level to debug and see everything that's going on. Or if you're just trying to run in maintenance mode and only the errors should be reported, you can set this to error. Now there is another scenario which you simply cannot handle with the print statements. Imagine that you have deployed this code onto your user's machine, and when they run it, they are going to see some print statements, and they probably close the console and you cannot see what's going on. So if you later on ask them, what did you try to do? They may or may not be able to tell you what went wrong. So what you can do is you can go ahead over here and add another option over here. So this is going to be file name is equal to, let's say, sqrt.log. So you do that, and now and let's go ahead and change this to debug again. So now when we go ahead and run this, it's only going to output the print statement that I have over here, right? So only this has been output, and we have not output the logging information even though the log level is set to debug. The reason is that all of that information is now sitting in this file name. So vi_sqrt.log, and you can see that all of that stuff is over here. And you can ask your users now to send you the log file so that you can take a look at what's going on, what went wrong, and how you can fix it. So this is essentially a run of your whole software. So if you have a problem, you can ask your users to send you the log file, and then you can simply look at what your program was doing instead of trying to communicate with the user and having them tell you, because in real life, your user will be of hardly any help. So this is a very powerful tool. And as you can see, it's extremely easy. You do import.logging, and instead of print statements, you do logging.error, logging.info, logging.debug, logging.warn. And you simply go ahead and save them to a file if you want that. If you're doing it yourself, you can output it to the console. Anywhere you want to work with this. Finally, if you want to study this in more detail, you can go to this URL and you can take a look at the logging how-to. So here's the basic tutorial, and then you can go ahead and read why it's useful. There's a simple example, and you can log to a file. You can log from multiple modules so that you can see what each module is doing. And there is a lot of stuff over here as well. Now, it's very important that you realize that these tools are not just there for explanation. If you start using them, they're going to make your life a lot easier, right? So whenever you write a program in the future, start using logging and you'll thank me for it. Right, so we are in this 02 folder, and here we have two files, basicmath.py and testbasic.py. So in this basicmath.py we have our code. So at the moment it's a very simple piece of code. So it's a division function which takes two numbers, divides them, and returns the output. So nothing special going on here, but you can imagine that this is some complicated piece of code which for instance makes sure that your payment is working fine. Right, so any piece of function that is there, you can have this in classes anywhere that you want, and what you want to make sure is that this works fine. Now this might look very easy to do and you can just eyeball it and see that yes, this is working fine, but imagine this scenario. Let's say you are in Python 2 environment. Now in Python 2 environment, if this code was written, then this would be an integer division and this code would be broken. So 4 divided by 3 is not going to be 1.3, it's going to be 1. So it's going to be broken if this is in Python 2 environment. So if your developer was somehow working in Python 2 environment and you wanted to deploy it in Python 3 environment, this function is kind of broken. So with this very simple example, you can see that some developer's environment is going to affect your production code. And for that, you need tests. So we have a very simple test over here, and here's how you do it. You have some piece of code in your environment. For instance, we have basicmath.py. Now what we want to do is you want to create another file. So this is called test_basic.py. So the convention is that your file name in Python should be test_. Again, this is not limited to Python. You can have very similar concepts in Java, in C, in almost any modern language. But since we're taking Python as an example, this is how Python does things. If you go to another language, it's going to be essentially the same concepts, but here's how Python does it. So you import your module from basic math, import div. So from this module, we're importing this div function, and then we are going to create a new function over here, which is called test div. So the name is not important, but it has to start with test_, right? So that's the convention of Python. So it has to start with test_, and then you can have anything. So we've named it test_div to let people know that this is testing the div function. Then what you want to do is you want to call this div function. So we've called it with div 4,2, and we want to assert that it does return the value 2, right? So that's essentially what it's doing. It's saying assert, make sure that div 4,2 is equal to 0. So this has to be true for this assert to be satisfied. Assert essentially makes sure that your assertions are met by ensuring that it gets a true. So if it gets a false, it's going to raise an exception, and we'll see how this works. So let's go ahead and run this. So in order to run this, you have to have PyTest installed. So if you don't already have this installed, you can say pip install PyTest and it would install it for you. But if you are following the Anaconda distribution as suggested, PyTest would be already installed. So what you can do is you can say py.test, and it's going to automatically read all the files which begin with test_. It's going to go into those files and it's going to find all the functions that begin with test_, and it's going to run them, right? So let's go ahead and do that. So as you can see, it's running and it has collected one item, which means there was only one test. So now you are in the situation where you are the QA engineer and you are testing whether the basic math module works fine. So at the moment it works fine. There was one test, it passes, and everything is fine. Right. So now let's go ahead and create another test. So this guy over here. So we want to make sure that the division of 15 with 3 returns 5. So let's go ahead and run this again. And you will notice that it now has 2 items over here. So imagine that this was somehow broken and we were multiplying instead of dividing. So if you go ahead and run that now, you are going to get these errors, right? So here's the problem. Assert 8 is equal to 2. So div 4,2 returned 8. And it's not equal to 2, so assert was not satisfied and it threw an assertion error, right? So it throws an exception if it gets a false. So 8 double equal to 2 or 8 does equal to is a false, and assert is not satisfied, so we get an error. So that's essentially the concept. You do something, you give it some inputs and you get the outputs, and you make sure the outputs are what you expected. So that's essentially how we teach testing typically. But generally, I've seen that people find it very difficult to understand what we're doing and why we're doing this, right? So let's fix this and go ahead and make sure that our code is working now fine. Yes, everything succeeds. So let's go ahead and take a look at another example, right? So we have this another function over here, which ensures that div of 1,2 is equal to 0.5. So you can go ahead and run this as well. So this returns pass for everything. So if you were in Python 2, this test would fail, right? So this takes care of our initial assumption. So let's go ahead over here and now do another function. So as you can see, this is a slightly more complicated function. What it does is it takes a list, creates a copy, sorts it, and returns it, right? So we have some function over here which essentially does the sorting, and then we return it. Now I know Python already has a sort function, but we're trying to create something that is a little more complicated, so we've created the algorithm ourselves. So let's go to test basic, and here we have some tests for this function. So here's the idea. You know that you have this list L, so this is some list with some elements, and you know that when you sort it in ascending order, it's going to look like 0, 2, 3, 6, 7, 15. It doesn't matter how it's sorted, that's what it's going to look like. And this is the very important concept of testing. You don't have to know how things are done. You just have to know that given this input, this operation should produce this output. So we know that given this input L, this sort list should produce this L underscore sorted, right? So we go ahead and run this now. So save both of these files, and let's go ahead and run py.test. Py.test, and you will see that the 4 items were collected, 3 for the div, and now this one new one for the sort list. And you will see that this is not fine. So this is what is returned by a sort list, and this is what we expected. And as you can see, we have an error over here, and just eyeballing it, we can see that it is sorting the list in descending order and not in ascending order as we expected. So even though our test guy does not know why this is failing, he or she is simply going to take this output assertion error, send this to me and say, your tests are failing, you need to fix them, right? So me as a developer then goes ahead and takes a look at this and sees that, oh yes, I have a less than sign over here, and I should have had a greater sign over here. I do that, I submit it, and it goes to QA again. QA people run this test again, and they're good, right? So that's essentially how things are going to work. So you write a test and you make sure that you understand what the inputs are going to be and what the outputs are going to be. You're not concerned with the method of how the input is transformed into the output. Once you have that, you run the test and you want to make sure that everything is working fine. Let's go ahead and do one final piece of code. So this is a function which opens a file for us, right? So let's say that for this file, we want to make sure that whenever this file is not found, our code should throw an exception. Now our developer is slightly more gung-ho, and what they decide is that they're going to check whether the file does not exist, and if it does not exist, they're simply going to return a null value over here. Now this does not correspond with what our logic is, right? What we want is that if the file is not found, this function should throw an exception. Now the developer has a different understanding. What they think is that the exception should not be thrown, and they're handling that exception by checking that the file does exist before trying to read it. Now they might have good intentions at heart, but that's not what we want. What we want is for it to throw an exception. So what we're going to do is we're going to write another test over here, and from here we're going to import this again, the open file, and what we're going to do is we're going to give it a file name that does not exist. So this is our test. This is what the QA people are doing. They are going to try to open a file, and they are going to raise an exception if this guy does not raise an exception. So if you are familiar with Python exceptions, you would know that if this portion over here, if this raises an exception, we're going to go directly to file not found error, and we're going to get over here and we will be fine. So if open file raises the exception of file not found error, we're good. Even though the exception has been raised, but because this is expected behavior, we are fine with this code. But if this open file does not raise an exception, then we raise an exception. That exception which was accepted has not been thrown, and therefore we are throwing this exception. So think about this. If the open file function does throw an exception, we're good. So if it does throw an exception, we go from line 43 to line 46 and then to 47, and everything is fine. None of the asserts fail, and we are good. But if the open file does not throw an exception, which is not what we want, we get to this line over here and we throw an assertion exception or assertion error over here, and that is going to make our test fail. So if the open file does not throw an exception, it's not good and we fail the test. If it does throw an exception, we're good. So I hope that makes sense. Please go ahead and read this code thoroughly so that you understand this. This is a very important concept. Now when we go ahead and try this out, py.test, you will see that this accepted exception is not thrown. So we tell our developer that you should have been throwing an exception and you're not. So the developer goes ahead and gets rid of this file. So they wasted their time. But once they get rid of that check, our tests are now successful and we're good. So please make sure that you understand this. This is one of those things that you have to understand if you want to go from beginner level to intermediate level, because that's how real professional software developers work. In this lecture, we are trying to cover two concepts. One is related to Python and the other is related to tool support, which will help you learn Python or a lot of other languages as well. So let's start. We are in our notebooks folder and in the 04, because this is the fourth lecture, and we are in the list_mutability notebook. So first let's go ahead and take a look at a very simple concept. So we have a variable x and we assign the value 34 to it. Then we say y is equal to x, and as you know, the value of x, which is 34, is saved into y. So if you change y later on, x is going to remain the same. So x is 34 and y is 20, and there is no relationship between y and x. So that's simple. Now let's go ahead and take a look at the same concept but with lists. So we have a list over here which is called mammals, and it has 3 mammals in it. So cat, kangaroo, and horse. And we have another list which is fish, and we have tuna, shark, and catfish in it. Now what we want to do is we want to execute that, and then we want to create another list which is going to be a list in which the first element is going to be this list and the second element is going to be the fish list, right? So once we have that, we have a list of lists, and the first element is a list which is mammals, and the second one is the fish. So now what we want to do is we want to change the value of the first element of the mammals list. So if we do that, we can see that the mammals list has changed, but so has the animals list. So how does that work? So if you're already aware of this concept, fine, we're going to build on top of this, but if you're not, we're going to cover this for the sake of completeness. And in doing so, we're going to introduce a very, very powerful tool. So this tool is called Tutor, Python Tutor, and you can access it at www.pythontutor.com. If you go over there, you will see that this is a tool that helps you visualize code and get live help. So it has been created by Philip Go, and if you click on Python Tutor, you are shown this interface, and we have already pasted the code over here, but you can go ahead and type it if you want. And this is the portion of the code that we want to take a look at. So you paste your code over here or type it, and then you go ahead and click on visualize execution. What it's going to do is it's going to create an environment for you which is going to visualize how each line executes, right? So you have this point over here which says that you are going to execute this line, and you can click on forward to step through your code. This is a very useful tool if you're trying to explain Python to somebody, if you're trying to do an introduction to Python, for instance, and you want to teach people how to learn Python, or if you want to learn some complicated concepts yourself. So this is a very useful tool which goes well beyond this particular lecture, but we're going to use it over here. So let's go ahead and step through this. So we hit forward, and what it does is in the global frame, it creates a variable mammals which points to a list. In this list, we have 3 elements, and each of them have their corresponding strings. All right, so that's easy. Then we execute the second line, and it's going to create another list which is fish. And here's where the utility of this Python tutor comes in. When we create this animals list, you can see that the animals list has 2 elements, and the first one is essentially pointing to the same mammals list, and the second element, which is element number 1, that is pointing to the fish list. So in the memory, the value of cat is only occurring once, and this animals list is only pointing to the existing list, right? So when we go ahead and change mammals 0 is equal to mule, so what we're going to do is go to mammals, go to the 0th element, and change this to mule. And when this changes, the animals list is going to be affected as well, right? So mammal 0, and you can see that this has changed to mules, and if you access animals 0 and then 0, this is also going to be mule. So that is essentially what's going on over here, and that is why this has changed to mule, right? So this is a very powerful concept, and it helps you understand how lists relate to each other and how different lists are composed together, right? So let's go ahead and build on top of this a little bit further. So we have another list over here, which is mammals 2, and we say mammals 2 is equal to mammals. And when we go ahead and change the first element, the 0th element of mammals underscore 2 to dog, you will notice that not only mammals 2 changes, but so does mammals. And also along with that, the animals list also changes, right? So let's go ahead and take a look at this again. So over here, so we create another variable mammals2, and we assign the value of mammals to it. So essentially what it's going to do is it's going to create another variable, but this variable is also going to point to the same mammals list. So if you change the 0th element of mammals 2, you're essentially changing this mule over here, which affects mammals as well as animals. Right? So if you change that, you can see that only one thing has changed, but because of the fact that mammals is accessing this guy over here, we have changed mammals as well. Right? So mammals has changed and so has the animals. Right. So, but does that mean that we cannot create a copy of the list? Up until now, we have only been assigning the same list to different variables. How do I create a copy? What if I need a copy and I want to change them separately, independently from each other? So the way to do that is to use this syntax. So you say mammals3 is equal to mammals, square brackets, and within it you are going to use the slicing operator. So essentially what it's saying is take all the elements starting from the beginning and going up until the end, take all of those elements and from them create a new list which is going to be called mammals3. So let's go ahead and execute this. And now when we change the 0th element of mammals3, you will notice that mammals and animals is not going to be affected, right? So mammals3 changes, but mammals and animals does not, right? So let's go ahead and take a look at this. So when you create a copy using this slicing syntax, what you're doing is you're creating a complete copy of this list. So this is now completely separate from this list, and therefore when we change mammals 3.0 to mouse, only this guy changes and this one does not, right? So right, that works, but this gets better. So let's go ahead and create 3 more lists. So we are going to have S1, which is going to have student 1's information, S2, which is going to have student 2's information, and similarly we're going to have an S3. So we run that and we create a new list of students which is going to have all 3 student lists in it, right? So we have this guy over here. So that's simple. Now what we want to do is we want to create a copy of this, and as we knew, we can use the slicing operator, and we do that. Fine, that works. Everything should be good. Now what we want to do is change the 0th element of the first student in the student copy. So we want to change this to student 1 changed. So this student 1 should go to student 1 changed, but we expect that this student, which is in the students, should remain the same because we have created a copy of students. But when we execute that, we see that this student's copy has this guy changed, but this student's also has changed. How does that work? Haha. So let's go ahead and take a look at this. So again, we're executing this. So here we're going to create S1, S2, and S3. Then we have a students list, which is going to have all 3 of these as its elements, right? So now what we do is we create a copy of students. So you will notice that what we are going to do is we are going to take all the values that are over here and we are going to create a copy of that named as students copy. But because these are pointers, these are addresses of these lists, what we're going to do is we are going to copy these addresses. And essentially the lists over here are not going to be copied, right? So notice this, students copy, it is different from this guy over here. So students and students copy is different. They are not connected to each other, but students copy, or the first element of students copy, is pointing to S1. The element 1 of students copy is pointing to student 2, and students list is also pointing to the same thing, right? So if we change the 0th element of the 0th element of students copy, we are also going to affect students, right? So if you do that, you will notice that this has changed, and because this guy is pointing over here, it's going to have the same problem. Now this is what is called a shallow copy. So what we've done is we have only copied 1 level deep. So these guys have been copied, but what they were pointing to has not been copied. What we want instead is to do a deep copy so that the students copy is completely decoupled from the students variable or students list, right? So for that, what we're going to do is we're going to use the idea of deep copying, and for that you need to import the copy package. So copy module is imported, and we say student3 is equal to copy.deep copy students. So when we do that and we change students 3 again, you will notice that even though students 3 has changed, the students list remains the same, right? So let's go ahead and run that as well. So there we go. We import copy and we say students 3, and we are going to deep copy this. So notice that we are going to create a new variable over here, students 3, and as you can see, it creates a deep copy. So this is copied and all the second level lists have also been copied. So these are now completely decoupled from the original data. And now when we go ahead and change this guy over here, it does not affect this guy over here. Right? So that's the idea of a deep copy, and it comes in very handy when you're trying to work with lists of lists. And it's not just in Python, it's a very important concept that comes up in almost all modern languages which have the concept of lists built in. Right, so let's finish this off by talking about a final concept. So we have a function change variable over here which takes one argument and increments it. In similar vein, we have another change list function over here which takes a list and appends 24 to it. Right, so let's go ahead and execute this. If we say x equal to 25, change var x and then print x, even though x is being incremented over here, we expect that this is a local variable, so it should not affect our x which is outside over here. So we execute that, so it remains 25 even though we incremented this over here. Right, so if you don't understand that, please go ahead and execute this in the tutor so that you do understand it. Now if we take our s2, which is this guy over here, so this is our s2, if we take that and we pass it to this change list function and this list is appended, we expect that this is a local variable, so our list s2 should not be affected. However, it is. So this s2 has been modified. So how does that work? So let's go ahead and execute this over here in our tutor. So we create a change var variable, a change list function, sorry, and then we say x is equal to 25. When we go to change var x, a copy of x is created, so 25 is copied over here, and when we change this x, this local variable x, local frame x, this gets incremented. However, the global x remains the same. So when we come back, our x is going to be 25, and that is what we're going to get as output. However, when we have this s2 over here, this is a list and this s2 is kind of a pointer to this list. So when we pass this to the change list function, we are going to create a copy of this variable. However, because this was pointing to this guy over here, this is also going to point to the same list. And if you change this list by appending 24 to it, you will notice that we have also modified s2 over here. So when we're back over here, our s2 has also been modified. So what it comes down to is the fact that if you have a list and you pass it to a function, you cannot be sure whether that list has been modified by the function. And if you are not the author of that function, you can never be sure what has been changed by the function. And that is why we have tuples. So if you remember, tuples are immutable. So if you have a tuple and you pass it to a function, it's guaranteed that the function will not be able to affect your tuple because tuples cannot be modified, neither by the function nor by you. And that is why we need tuples. That is one of the reasons why we need tuples. So if you have some data and you want to pass it to a function and make sure that the function cannot modify that, you use tuples. If you want to allow the function to modify your data, you use lists. So I hope this lecture has given you an understanding of how list mutability works, what deep copying and shallow copying is, and above all, you have gotten used to using this Python tutor to understand the concept of complex interactions between different variables. Try it out and let me know how you like it. So generators are such an important concept that they get their own syntax in Python. So let's go ahead and take a look at this syntax, and in doing so, try to understand the computational power that comes with generators. So we have this statement over here. So this is a list comprehension. So I square for I in range 1000. So this is going to turn this into a list, and as you can see, we have square brackets over here, and this goes into V. So what this means is that we are going to create 10 million square numbers, and this is going to be a huge list, and it's going to take up a lot of time to compute. So we have this %time magic command over here that is going to compute the time that this takes. So this is going to take a while, and as you can imagine, this whole thing is going into memory. So this is going to take up a lot of space as well. So if we have such a huge list and we want to compute that, even though it's a very simple list, it takes 6 seconds to compute. And as you can see, all of these are in memory, we can index them and everything. If on the other hand, we don't want this stuff to stay in memory, but we want it to be generated when we need it, we can use, instead of square brackets, we can use parentheses over here, and that is going to convert this into a generator and not a list. So this whole thing is exactly the same thing, except it's going to be a generator and it's going to be saved in G. And we have the %time over here, and as you will see, this is almost instantaneous. So 15 microseconds. The reason is that G has not really computed this value over here. It's going to compute it when we need it. And that's the power of generators. We tell it what we're going to need in the future, and it's going to compute it for us as we need them. So you can have G over here, and you can then go ahead and say next of G, and it's going to compute the value. So 0, 1, 4, 9, 16, 25. You can go up to 10 million as many times as you want, except you don't have to keep everything in memory. So that's the power of generators. So let's take another real world example. So for instance, you have a file which is called access log, and this looks like this. So this is a real world web server log, and each line represents one request that this web server gets. At the end of this line, this value over here is the number of bytes that have been transferred for this request. What we want to do is we want to take up all of these values and sum them over so that we know how many bytes were transferred. Right? So that's our use case. How would we do this? Typically, let's do this without the generators first, and then go ahead and see how generators can make our code look much prettier. So we have this file over here, www.log is equal to open this file, and for each line in this file, we're going to print the line and we can break it. So this is what this looks like. This line looks like that. Now what we can do is we can open this file again and save a total count over here, which is going to be 0, and read each line and convert the line by splitting it, and then taking the last value from the split and saving it in byte str. If it is not equal to a dash, we are going to increment the integer value of this byte string. So the reason for this is that sometimes you might get a dash at the end, for instance this guy over here, and this might lead to problems. So we have this check over here. So at the end we print the total. That's how we do things typically. So if you do that, you will see that this is about this number. Now the same idea can be implemented using generators in a very concise, very clean looking, beautiful code. So the first line is the same. So we're going to say www.log is equal to open this file. Then we're going to create a generator. How do we know that this is generator? Because we have parentheses at the beginning and end. And what we're going to do is we're going to say line.split. For each line in www.log, we are going to get this byte column out. So notice that because this is a generator, this line is not going to go ahead and loop over the whole body of the file. It's going to only open the file when I try to read this file, and I'm not trying to read it at the moment. It's a generator that's just going to be sitting there. And then we have this another generator which takes all of these byte columns. If they're not equal to dash, it's going to convert them into integers. So again, it's converting stuff into integers if they're not a dash, but still it's not actually doing any processing right now. What I'm doing is I'm giving it my specifications, what I want, and when I actually try to compute the things, then it's going to go ahead and read the file. So up until now the file has not been read, and when I say sum of bytes, it's going to try to read the bytes, and in trying to read the bytes, it's going to call this generator, which is going to loop over this byte column, and when it loops over the byte column, it's going to ask this generator to read them one by one, and when this tries to read the line in www.log, it's going to open this file over here. So it's going to happen when it's needed. So if you do this, you will see that we get the same result out, but the code is now just 3 lines of code and very precise, and it tells you what you're trying to do because it has a very clean syntax over here. So I know that this might look a little weird and you might think that this over here is much cleaner code, but believe me, once you get into the habit of using generators, they really give you the power of not having to load everything in memory, but at the same time being able to specify your code very cleanly, right? So at the end, let's try to do a case study that is going to be extremely difficult if you don't do it with generators. And the idea is that we want to tail a file. We have a file, and what we want to do is we want to tail a file in the sense that whenever something is added to that file, we should be able to see it, right? So this might be useful if you are trying to compute the statistics of a web server, or if you're trying to do anything on a file that is changed periodically and you want to tail the file. It's called tail. It comes from the Linux environment, and it's a tool that is used very often by system administrators. So what we do over here is we import time, and we have a function over here which is follow, and because it has a yield over here, that means that this is a generator. Now this takes a file, and what it does is it seeks to the end of the file, and then it goes into an infinite loop. What does this infinite loop do? It tries to read the line, and if it does get a line out, then it yields that line. If it does not get a line out, then it goes to sleep, and after 0.1 seconds it comes back and tries to read the line again. So essentially, try to read the line. If there is a line, yield it. If there is no line, then just wait for it, right? So there you go. And what we're going to do is we're going to open a file over here, which is test log. So it's an empty file, and log lines are going to be follow log file. So because this follow is a generator, this log lines is going to be a generator, right? So let's go ahead and check that. So the type of log lines is a generator. So it hasn't actually opened the file yet. Even though I did say follow log file, it has not opened the file yet. Instead, when we try to loop over this log lines, then it's going to go ahead and call this function, and this function is going to start executing, and it's going to get to the yield line, and then it's going to stop. So I say print line comma. So I want to print this line, and I want to make sure that I can stop, because this is in an infinite loop. I want to make sure that if I put just a dot in the file, then the whole loop is going to break. So let's go ahead and run this. As you can imagine, it's not outputting anything over here. So let's go ahead and echo something to test log. So if you do this, you will notice that this appears over here, but the function is still waiting. So let's go ahead and input something else. So something else to test log, and that goes over there as well. But if I say echo dot to test dash log, our function is going to exit over here. So please go back and try to reason about these. In one of the future videos, we are going to take a look at how generators lead to a very powerful construct of asynchronous programming. But for now, it should be sufficient if you understand all of this concept. So we are in notebook/06, and this is higher order functions. So as before, let's go ahead and take a look at the concept first before defining it. So we have this very simple statement that you've come across a lot of times. So x is equal to 24. What this means is we have some piece of data which is 24, and we're simply giving it a name x. So we want to use x to refer to 24. So simple concept. Take this concept to the next level, that we have this function over here which takes an input x and returns the square of it. And we're giving it the name of square. So this name could have been s, it could have been f1, it could have been anything. We just happen to name it square because that's what makes sense. So let's go ahead and run that. And if we say square of 6, it's going to say 36. So that's pretty common. However, if we say just square, it's going to evaluate this to a function. What this means is that the word square itself points to a function. We'll see this visually in a minute. Because this square is a variable and it points to this function, we can also say f is equal to square, just as we could have said y is equal to x, and y would have pointed to 24. Now, if we say f is equal to square, f is going to point to the same function over here. So if we do that and we execute it, you can see that this function also points to square. And if we say f of 6, it's going to return 36. So f is just another name for square. Let's look at that in our tutor. So if we say a is equal to and this list, it's going to create a list, and a is going to be a variable that's going to point to this list. If we say b is equal to a, it's going to be another variable, but it's going to point to the same list. So we covered this in the previous video. Now, if we say def square x and define the function, it's going to be the same idea. We have a function over here, and this variable square is pointing to it. So if we say f is equal to square, same idea, another variable f points to the same function. So essentially these two are exactly equivalent. This function just happens to have its built-in name called square, but it doesn't matter if we access it through square or f. So simple concept. Let's see how we can use it. So we want to write a function for calculating the sums of I square from I is equal to 1 to 10, right? So we want to square 1 square plus 2 square plus 3 square and return that. How do we write this function? We define a summation function which takes a low, which is going to be 1, and a high, which is going to be 10. And we're going to keep a count of the total, and we go from low to high plus 1 because it's going to stop at high if we give it the range of low to high plus 1. Then what we do is we calculate the value that is going to be this guy over here, I square, and we increment the total with it, right? So that's how it's going to happen. And at the end, we're going to return the total. So very simple function. And if we say summation of 1 to 3, it's going to be 1 square plus 2 square plus 3 square, which is going to be 14. Now, if I want to write another function that instead of doing I square does I cube, what I'm going to have to do is write another function which is going to do essentially the same thing, except this is going to be I cube instead of I square now. But what's the difference between these two functions? As you can see, the only difference is that this val value is changing. So how can we generalize this? So let's first go ahead and define two functions. So square we already have. Let's define another function cube, and this is going to return the cube of x. So let's run this. And now I'm going to define another function summation, which is going to take not only the low and high, it's also going to take another parameter, which is going to be called fn. Now this fn is going to be a function that we are going to call on this I over here. So recall that this val is computing the value that is in the body of the summation over here. So what we want to do is whatever function is passed to it, we are going to use that function and we're going to call it on the value of I. So let's go ahead and run this as well. And let's say summation 1, 2 and square. So 1 is going to go to low, 2 is going to go to high, and the square is going to go to fn. So recall from up over here that we can simply say f is equal to square. Similarly, here we're saying fn is equal to square. So fn is essentially the same function as square. So if we go over here and we loop over this body and we call this fn, so essentially what we're doing is we are calling square on this value I. So in the first iteration of the loop, this is going to be square of 0. So a square of 1, sorry, we're starting from 1. So square of 1, and that is going to go into the val. The second time it's going to be square of 2, and the third time it's going to be square of 3. So essentially what we're doing is we are using this idea of treating a function as a piece of data and using different variables to point to the same piece of data. So we can do that. So now if you have this function over here, there is this beautiful concept that what you can do is you can simply use the same function of summation and pass it another function cube, and it's going to compute the cube's value over here. So for these two functions, I square and I cube, you don't have to write another piece of code. You just have to define how to compute this guy over here, and the summation portion is now done. So please execute this, take it step by step and make sure that you understand. It's not a complicated concept. It's a very simple concept of having two variables pointing to the same function, right? So let's take it another step. So we can also say summation 1, 10, and then we have this weird looking guy over here. So if you haven't seen lambda notation before, let me explain it very briefly. So lambda I essentially means that this is a function which takes one parameter, which is going to be called I, and it returns the value of I square. So it's a very simple idea. It's another way of writing a function. Instead of def, we say lambda I, so that is one input, and it returns this statement over here, right? So I square. So this is essentially the square function, and it's called an anonymous function because it does not have a name. Even though by looking at it, we can see that it's a square function, but it does not have a name. Therefore, it's called an anonymous function. So that's the idea of an anonymous function. They are used a lot in a lot of programming languages, and you will come across them if you program at the intermediate or expert level. But here's the idea. Essentially, summation 1, 2 and square is the same as summation 1. Let's make this 2. Let's make this 2. So summation 1, 2 and this guy lambda over here is essentially the same because square is squaring and so is this function over here. So now we can run this and it's going to give us 5. Now, an important thing to notice over here is that this piece of code looks very, very similar to this mathematical notation over here. So we have summation, so this guy over here, I is equal to 1. So starting from 1, going up till 10, or going up till 2, same idea. And then we have this body over here, which is defined using this function, which is an expression. So it looks very similar to the mathematical notation. And if you have some piece of mathematics, now you can translate it very easily to this piece of code. So what if we want to write another function for this guy over here? All we have to do is say summation 1, 10, and lambda I 2i square, right? So we are going to get the 2i square value over here. So this is the idea, that you have a function, the summation function over here, which can take in another function as an input parameter. So a function that takes another function as an input is called a higher order function, because it's a function that works on other functions. So this is the idea of a higher order function, and it is an extremely important concept, and it comes up again and again. And in the next video, we'll see how this concept can be used to bring together another very important concept that is very often used in programming languages such as JavaScript and other modern languages. So we're doing higher order functions. What we want to do is we want to take a look at a case study and through it explain another very important concept. So here's the simple idea. We want to define a square root function. So this square root function takes the number for which we want to calculate the square root, and it also takes an optional parameter, which is guess. So if guess is not passed to us, we take it as 0.1. So that's the default argument part. That should be clear. Then what we do is we have a very simple algorithm over here. We check if the guess is good enough as a square root of x. If it is good enough, we return it, right? So for instance, if by chance I happen to have a guess of 6 for the square root of 36, it's going to be good enough and I'm going to return this. But that's almost always never going to be the case. So if that isn't the case, what do? I improve the guess somehow by taking the old guess and the number for which I want to calculate the square root and pass it over here, right? So if I have this guess, then I use this new guess to calculate the square root. So this is an algorithm that comes from Heron of Alexandria, and you can take a look at the details of this on this page over here. I'll give you a link of this, but essentially the idea is start with a guess. If it's not good enough, divide your original number by your guess and then average the two. So this average is guaranteed to be a better guess than your original guess. So it's not important how this is working at the moment. All we want to do is we want to make sure that we have some idea of what good enough is and how to improve the guess. So good enough essentially means that if you take this guess and you take this x, if you square the guess and you subtract from x, so if you have, for instance, the guess of 5 for the square root of 36, so 5 into 5 is going to be 25, and if you subtract 36 from it and take the absolute value, it's going to be 11. So is 11 less than 1? No, it's not. That means that the guess is very far away from our actual answer. However, if you have 6 as the guess, you have 6 into 6, which is 36, minus 36 is going to be 0, which is less than 1. That means our guess is good enough. So as our guess goes closer to the actual value that we're looking for, this value is going to go towards 0, and we are going to get our guess to be good enough. So what we want to make sure is that it's fairly close. So if I say less than 1, it means it's less than 1, the error is less than 1, and it's acceptable to me, right? So that's my definition of guess at the moment. We'll run this in a minute and see how this works out. The other idea is the concept of improving the guess. So again, we take the average of guess and the division of the original number by the guess. So it's not important what the algorithm is, right? So let me say that again. It's not important how the algorithm works. All you must understand is that we are starting with the guess. We are checking if the guess is good enough. If not, we're trying to improve it. And we continue doing this until it does become good enough. So that's the idea. So let's go ahead and run this. And because we have a print statement over here, it's going to tell me what guesses it's trying. So let's go ahead and run this. So it starts with the guess value of 0.1, and the value that we get as a result of guess into guess, that is going to be very far away from 36. So it's not good enough. We try to improve it by dividing 36 by 0.1, and we get this new guess of 180, and that's still far away. We take the average again, and our new guess is 90. And as you can see, we keep going until we get to 6.002. Now this 6.002 isn't actually the square root of 36. We know that, but the computer does not know that. Why? Because we are calculating over here. We are saying if this is good enough, and our good enough function says that if the difference between these two is less than 1, and over here the difference between these two indeed is less than 1. So 36.02 is pretty close to 36, right? So the difference is less than 1, so this is acceptable for us, and we have this value as a result. Now, what we're trying to do over here is, instead of hard coding this idea of good enough over here, so currently this good enough is a function that is a very specific function. It has a very specific definition. So our square root function is going to work for people who don't care about the square root being too accurate. For instance, the weather people, if you have the end result of your weather prediction off by 1 degree, it doesn't make much of a difference. But if, for instance, you are in a nuclear reactor and you want to make sure that your square roots work very, very, very closely to the real value, for instance, up to the 15th decimal place, this is not going to work for you. So what we do is we define this good enough as a parameter. So this isGE is going to be a function parameter. Just as we had fn over here, this isGE is going to be a function parameter. We just happen to give it the default value of good enough. So if we don't pass in an isGE, it's going to use the good enough function. If we do pass it another function, it's going to use that. So we change this good enough to isGE, and now because we have this good enough over here, that is going to be used. So it's essentially the same idea until now. However, let's say the nuclear reactor people come up with a different good enough function, which is very accurate good enough, and they say that our difference should be up to this level of accuracy. So they can define that, and then we can say square root and isGE is equal to very accurate good enough function. So if we do square root of 36 with this new function, it's going to go ahead and calculate this. So we stopped at this point last time, but now we are going to go to 36.000005, and then even this isn't acceptable for us, so we improve it again and we go up to this many levels of accuracy, and now our square root is very, very, very accurate, a lot more accurate than this guy over here. And you will notice that we did not have to change our function. So if somebody comes up and they say that even within an accuracy of 1 order of magnitude is fine for me, then it's still going to work for us. So this is the idea of having function pointers or function names and passing function as parameters. And the idea is that this variable isGE is termed as a callback. So essentially what you're doing is you're passing a function into another function, and that function, this guy over here, is calling the function that you pass to it. So essentially you are allowing it to call you back, and that is the concept of callbacks, and it is used a lot in JavaScript. For instance, whenever you have an Ajax call and you say that whenever the response comes back, you execute this function, for instance, to display it on the web page. So this is the idea of a callback. Pass a function to another function, and that other function calls your function back when certain conditions are met. And this is a very important concept, and it helps you out by writing a lot of very clean code. It does turn into more problems, but we'll come to that in one of the future videos. In the next video, we are going to take this concept and build something a lot more powerful on top of it. Once you have a good understanding of higher order functions, you can do some really interesting stuff with it. Let's start with notebook/07, and here we have decorators.ipynb. Let's first take a case study as always, and then try to explain what decorators are. So recall the typical Fibonacci series. So Fibonacci series is used in many places, but here we're not concerned with the uses. Here we just want to see what the series is. So it starts with a 0 and 1, and the next term is going to be the sum of the previous two ones. So Fibonacci of 0 is 0, Fibonacci of 1 is 1, Fibonacci of 2 is 0 plus 1, which is 1, Fibonacci of 3 is 1 plus 1, which is 2, and so on and so forth. So here's the mathematical formula for that. So fib of 0 is equal to 0, fib of 1 is equal to 1, and beyond that, every fib of n is the Fibonacci of the previous term and the term before that. So the previous two terms added together makes the next term. So that's the mathematical definition. So we want to take this into code. It's very simple. We define fib of n, and if n is less than or equal to 1, we return n, which is going to be this case over here. So fib of 0 is going to be 0, fib of 1 is going to be 1, and if that's not the case, then we return the sum of the previous two terms. So that takes care of the whole mathematical definition. So let's go ahead and do that, and just for fun, let's make sure that it's working fine. So fib of 0 is 0, fib of 1 is 1, and fib of 2 is 2, fib of 3 is 2, fib of 4 is 3, and so on. So it's working fine. So let's get rid of that. So now what we want to do is we want to time this. How long does it take? So let's run that. So we're trying to calculate fib of 35, which is a fairly large number, and it's supposed to take a lot of time because of the way we've coded it. and just 35 takes 6 seconds. That's really slow because fib of 35 isn't that large of a number. So it's not even 10 million, but it's very slow. And if I put this to 36, this is going to go to like 9 seconds, and I wouldn't even be able to do fib of 40. So when you're at home, try to time fib of 40. It's extremely slow, and we want to figure out why that is. Remember why we're doing this? We're trying to figure out how to use decorators, right? So it's intentionally slow at the moment. We can go ahead and take a look at the details of Fibonacci to see what's going wrong. So let's take a look at this Fibonacci of 6. So when we want to calculate the Fibonacci of 6, we want to calculate the Fibonacci of 5 and 4. When we want to calculate the Fibonacci of 4, we want to calculate the Fibonacci of 3 and 2. In order to do this, we need to do both of these. Then in order to do this guy over here, we have to do both of these. Then on the other hand, remember that we were trying to do f of 6. We did f of 4. Now we go and do f of 5. So f of 5 requires that we have f of 4 and f of 3. So we compute this again. But notice that we are trying to calculate f of 4 again, even though we have already done it before. So we are doing the same thing over and over again. So here we're doing f3 again, even though we had done it previously. So here we are doing f3 once again and f2 once again, even though we did it here and we did it here and we did it here. So when you try to calculate f7, you are going to do f5. So this whole tree is going to be repeated, and you're going to do f6, and this whole tree is going to be repeated. So you're doing everything many times, right? So that's the problem over here. Please make sure you understand this, that when you're trying to do f6, you have to do f4 and f5, and within f5 you have to do f4 again. So you're essentially repeating this whole tree over here, and this tree over here is being repeated over here as well. So this leads to the problem of repeated subproblems, and you can study this in algorithms and come up with a very complicated dynamic programming algorithm. There are many ways to solve this. You can come up with an iterative algorithm, but the way we want to do this is we want to keep this same definition of Fibonacci and speed it up, right? That's the idea. If you change the algorithm, this thing is going to change over here, and it's not going to look like the mathematical definition. So we want to make sure that this stays as it is, so that it's very clear what it's doing, and still make it speed up a lot, right? So that's the goal. Here's how we're going to do it. Before we do that, let's go ahead and take a look at a different concept, and we'll come back to Fibonacci in a minute. So we have this function over here, logger, and this takes another function as input. And you will recall that this makes logger a higher order function because it's taking a function and it's going to work on that. So what we're trying to do is, within this function, we are defining a new function. So this is an important concept in Python. This is not the case in many other languages such as C, C++, or Java. There you define the code at compile time and then it's done. You cannot create new functions at runtime. Here what we're doing is, when we call this logger function, we are going to be defining a new function called wrapper. So this function is not being defined right now. When we do call logger, then this function is going to be defined, and this function, this inner function, is going to take at some point in the future a number n, and what it's going to do is it's going to print this statement. Then it's going to call this f. Where is this f coming from? So this f is going to be the guy that we pass to logger over here. So we'll run this in a minute and we'll explain this in more detail, but at the moment remember that f is going to be some function that is going to be passed to logger. So this f is going to be called, and this n that we pass to wrapper is going to be passed to it, and whatever the result is returned by f, that is going to be saved in v. Then we print the second statement, which is the value returned by f, and then this inner function wrapper is going to return the same value that was returned by f, right? So we're going to run that in a minute, but we are still here in the logger function, and once we have defined this function, we want to return this function itself. So recall that wrapper is just a name of the function. So what we're returning over here is not the value returned by the function, but the function itself. So let's go ahead and try to visualize this in our Python tutor. So we have the def fib over here. So fib gets defined. So remember that fib is just a name for this function, right? So we have logger, and this takes one input f. Notice that this function has not been executed at all. We just defined this function and we're here now. This wrapper has not been defined, it's not over here. Now we call log fib is equal to logger of fib. So we call this logger function and we pass this function fib as f over here. So we do that. See, f now points to the same function fib. Then we go ahead and execute this logger function, and here we have a def function which is going to define a new function which is called wrapper, which takes one argument n. And notice over here that we have parent is equal to f1, so this f1 is the logger function that we executed just in the previous statement, right? So now we are going to return wrapper. So when we return wrapper, this is the return value, and that goes into the logged fib. In the global frame we have logged fib, and that points to this wrapper. And also notice that this f1 logger is now staying in memory. It's not going away because it needs access to this f and wrapper and everything else that is over here as well. Now let's go ahead and call this logged fib function. So this logged fib function is a new function, which is this guy over here, which has a parent of f1. Take this one step at a time. I know this is slightly confusing the first time you do it, but this is an extremely important concept and it's going to come in handy in understanding a lot of other concepts as well. So let's call this logged fib of 1. What we're going to do is we're going to go to this wrapper function and execute it, passing in the value 1 as this n, right? Because that's what this function is. This wrapper n is the logged fib function, and we're calling it, and we're going to pass the value 1 as n. So we go over there, n is 1, the parent of wrapper is f1, which is this guy over here. So we go ahead and execute this. So it's going to print this statement over here. There you go. So I'm going to call a function. Then what it does is it tries to call f. So what is f? We try to evaluate f over here. It's not available in the local frame, and the rule is that you try to go to the parent. So parent is f1, we go to f1 and see what f is. So f is this guy over here, and that points to Fibonacci. So we're going to call Fibonacci of 1 because 1 is the value of n over here, right? So we call Fibonacci of n and we go to fib. Notice that even though we called f, we have gone to fib because that's what f is. So we go over there and we execute fib as always, and is less than or equal to 1. So we're going to return the value of 1, and that value is going to go to v over here. So there we go. So v now has the value of 1, and we're going to do this second print statement. So there you go, the function returned 1. And then what we can do is we can return this v over here. And this v value is 1, so we're going to return that, and that is going to go to this calling statement over here, right? So everything else is still staying in memory. This f logger is still staying in memory because we have this logged fib in memory as well. Now let's go ahead and run this, and hopefully you should be able to understand it now. So def logger, when we say logged fib is equal to logger fib, we are simply going to create a new function. We haven't called fib at the moment. Now when we call log fib of 4, it's going to execute fib of 4 and return this value, but before doing that it's going to call this, and after doing that it's going to print this statement over here. Now what we have done is we have enabled ourselves to do stuff before calling a function, right? So we did this very simple print statement over here before we called fib. So we have logged the execution of fib. Now what we want to do is we want to take a step further and make sure that when we have this statement over here, this condition over here, we want to make sure that if we have computed f4 previously, we should save it in memory. So whenever we compute the Fibonacci of some number, we're going to save it in memory, and if it's needed in the future, we're going to use that from memory instead of trying to recompute it. So in the next video, we're going to try and do that. So in the previous video, we created this logger function over here, which took in fib and logged its execution. It didn't do anything else. It just logged that I'm going to call it. Then it said that the function returned this value. Now what we're going to do is we're going to create a new function, which is Memoize. So this is essentially the same as the logger function over here because it defines a new function, which is the wrapper. So we're going to call that wrapper Memoize function. It's typically called wrapper, but here for understanding, we're calling it Memoize function. It's also keeping a dictionary over here, which is going to act as a memory. So as before, this Memoize function is going to take the value of n for which we want to compute the Fibonacci series. And what we're going to do is we're going to first check if n is not in memory. So if you don't have this in memory, as is going to be the case when we start this, we want to compute the Fibonacci of n and then save it in memory so that it's accessible later on. Then we want to return this value over here. So this is what the memoized copy of the Fibonacci function is going to do. Then what we want to do is we want to return this memoized function so that we can say stuff like fib is equal to memoize of fib. So what this is going to do is, you can try to do this in the tutor again, but I'm going to try and explain this over here so that you are more comfortable with this without the tutor. So we define memoize and then we say fib is equal to memoize of fib. What this is going to do is take the fib function put it as f. Now this f is fib, so is this f, right? So now you can think of both of these f's as fib, right? So here's what Memoize does. It takes an f as input, so we're going to pass Memoize of fib. So we've passed fib as f, so read this f as fib and read this f as fib. The second thing that this Memoize does is it defines a wrapper function, and what this function does is it checks if we have something in memory. So it checks whether we have this fib number in memory. If we do have it in memory, then we simply return it. If not, we're going to call fib of n so that we can put it in memory now. And then we return this function over here. So when we say fib is equal to Memoize of fib, it's going to go ahead, define this function, return that function, and we have this Memoize function in memory now as fib and not the old function, right? So let's run that. And let's run this again. Notice that this is almost instantaneous because these are like 5 statements. Now when we say time fib of 36, it's going to take 8.64 milliseconds, right? So it took 6 seconds earlier and now it's taking like 8 milliseconds. So that's a huge amount of speed up, right? So I'm not sure about this number. Maybe this is for a fib of 40, but still it's a huge memory speed up, right? So this is exactly the same as we had over here. So instead of the wrapper, we have Memoize function, and instead of having print statements, we have this checking whether stuff is in memory. Now what we can do is we can go ahead and compute the fib of 40. So 27 microseconds. You can even go ahead and compute the fib of 100, and that's a huge number, and it would simply not be possible with the recursive definition that we had earlier over here. Now we want to add just a little bit of syntactic sugar on top of this, and we're going to do essentially the same thing. So this is the same Memoize function that we had earlier over here, and we have the same fib function over here. Instead of going through this route of saying fib is equal to Memoize of fib, we can simply go ahead and say at Memoize, right? So when we define fib, we can say at Memoize, and this fib function essentially gets put into this Memoize function. You get the wrapper back and you assign that to fib again. So this is called a decorator, and this statement essentially equals fib is equal to Memoize of fib after defining this function over here. So we can go ahead and do this and Memoize of fib, and if we say fib of 50, this works really well, right? So the idea over here is that we have a higher order function which takes a function and it performs some operations before calling that function, and then you take this modified function body, so kind of a patched function, and you save it as the same name as the original function. So when you call the original function, essentially you're calling this patched version of the function. So this is a very important concept, and it comes in again and again in modern programming languages. So this is type of a function annotation, and this is called decorator. So you've covered 2 concepts over here. Number 1, patching functions, which is called essentially decorating functions, and you've covered the concept of function annotation. So you're taking this function and you're annotating it so that it's modified at runtime through some dynamic behavior. Now what you can do is you can Memoize almost any function that has this property of repeated subproblems. So please make sure that you go ahead and run this piece over here in the tutor and map this to the logger function that we did earlier. To finish this video off, we're going to take a look at an example of how this decorator is used in real life. So you might have heard of Django. This is a web framework for Python, and it's extremely popular, it's extremely powerful, and it's a great way of learning the MVC paradigm and a lot of programming concepts. So here we have a login decorator, so login required decorator. What it does is whenever you have a view, so this is the function that creates web pages for people. So for instance, if you go to check your mail, this my view might be responsible for generating the whole mail view for you. All we have to do to ensure that only logged in people can view this page is to put an at login required decorator, right? So that takes care of everything. So it goes ahead and checks whether you have a session, whether you were successfully logged in before, whether you have cookies and stuff. All of that is taken care of just by putting at login required decorator over here. So essentially it does the exact same thing. It takes this my view, puts it in this decorator, which is going to be login required decorator. It checks a lot of conditions, whether you're logged in, session, etc, etc, and if it does, it returns true. Otherwise it redirects you to a login page. So it's a very real concept, and it's used a lot of the times in modern Python programming and even in other programming languages. So make sure you understand this, and it will allow you to really save time in a lot of programming tasks. Once we have an understanding of decorators and generators, we can do some really cool stuff that will save you time and make your code look really clean, which is one of the hallmarks of a great programmer. So we are in notebook/08 and the topic is context managers. So as before, let's start with something that you would already be familiar with. So opening files. What you do is you say f is equal to open some file name and then the mode, and then for line in f, you read each line, print it out, do something with it, and then you close the file. The problem is that people usually forget the closing of the file, and that leads to memory leaks and slowing down of your programs. But despite all the recommendations, people will forget to close the files. So the solution that Python came up with is to define a context manager. So instead of saying f is equal to open, you say with open this file as f, and then you do the processing on the file. What with does is that once you're done, once the block of with is done, it is going to perform all the cleanup, all the housekeeping that is necessary for this file automatically. So it's going to take care of closing of the file, freeing out the resources, whatever is needed, right? So that's the idea of a context manager. So this with keyword marks a context, and the block of this with keyword is going to be the context that is going to be executed. And at the end, it's going to ensure, according to whatever was done over here, it's going to make sure that the cleanup is done. So the general idea is this: you require some setup, then you do some processing, and at the end you require some cleanup. So whenever you have that pattern, you can use the idea of with and the context manager. So let's go ahead and take a look at a case study. So consider the case where you have some function which does some processing. So we've just put a time.sleep over here to show that it's doing some processing. So the working of the function is not that important. So in notebook, we've already seen %time some function. You can do that to calculate how much time it takes. But this is specific to the notebook. What if you want to do it in your own programs? So the way you do this is that you save the start time using this piece of code, and you do some function, and at the end you save the time again, you calculate the difference, and you print it out. So that's the idea. The problem is that even though this code is pretty simple, it's different from your business logic. So your business logic is just this one line, and everything else is just making your code look ugly. And this is going to be done again and again if you want to profile your code at different points in time. And it fits the pattern. You're doing some initial setup, you're doing some cleaning up and other miscellaneous stuff at the end, and in the middle you're doing some processing. So this fits the idea of a context manager. So let's go ahead and create a context manager for us. And the idea is very simple. From context lib, you import the context manager, which is a decorator. This decorator is essentially going to mark your function that you define over here as a context manager so that you can use it with the keyword with. We define a context manager and the name is timeIt. What we do is this is going to be the start of the context manager. So this is going to be executed whenever we do with timeIt. And then we have this yield over here. So if you remember this guy from the generators lecture, when the function gets to this yield over here, it's going to return, but it's going to save its state. And once the with block has been executed, we're going to come back to this function and we're going to execute the rest of the stuff. So the idea is very simple. We use it with, and let's go ahead and run this. So we use it with, and we say with timeIt. So what it's going to do is, what with is going to do is it's going to call this function timeIt. It's going to go up until yield. When this function yields, it's going to save the state of this function timeIt, and then it's going to drop the control over here. The with block is going to execute all the statements that are within this block. Once they have been executed and with is about to exit, it's going to go back to this function and it's going to continue from this yield line over here. And with this particular context manager, it's going to print the elapsed time over here. So let's go ahead and run this with timeIt some function, and you can see that we are getting the execution time over here very easily. So this code is extremely clean. It has our business logic very clearly put over here, and all the timing logic has been abstracted away in the timeIt code. So very clean code, and not only is it clean code, but it's also going to save you a lot of time. So let's say you have another function over here and you want to time that as well. So you don't have to write the context manager again, obviously. You can simply say with timeIt and you say another function and it just times it for you. So now you have a context manager that does timing for you, keeping your business logic clean, creating very clean code, and it also saves you time. In the next video, we're going to take a look at another case study which is very common as well. So in the previous video, we took a look at context managers, and here we're going to take a look at another case study for context managers. So the idea is that there are a lot of cases in which you want to create a temporary directory, put some files in there, process those files, and then get rid of those files. So if you're coming from a data processing pipeline, you might want to clean up some data, put it in the files, and once you're done with them, you want to delete that directory so that it's gone and it's not taking up space because you don't need it any longer. So the way we do this is that we have the temp file package, which is going to create the temp file for us, and then we have the shell utils, which is going to help us delete this later on, but we have to create the logic around it. So here's how we do it. We have to put this in try and finally blocks, because if we want to create a file and we want to open it, we might have some exceptions and we want to make sure that the directory has been deleted at the end. So essentially finally takes care of that. So whatever happens in between this portion over here, finally is always going to execute, which is going to ensure that the directory has been deleted and it's not creating garbage in our file system. What we do is we go ahead and create a temporary directory and save the name over here. Then we output where the directory has been created just for administrative purposes. Then we create a file name, which is going to be some file.txt within this directory. So just as a side note, never join your paths using backslashes or forward slashes. Always do them using os.path.join. But if you've come from a good Python course, you should already know that. So if you don't, please do look up os.path.join and always make sure that you join paths using os.path.join and not with some directory separator according to your own operating system. Anyway, so let's come back. So once we are done with this creating of the file name, we open the file name, we do some processing on the file, and once we're done, we want to make sure that we delete this directory using shutil.rm tree, which is the removal of the tree, right? So kind of rm minus rf. Anyway, so we have this idea over here and it's very simple, but the problem is that we have to do it many times, and this is completely separate from our business logic. Our business logic is just this one line over here, and we have a lot of stuff going on over here, which is simply for the purpose of creating the temporary directory and then deleting it later on. So this is a very common design pattern and you want to do it a lot of the times. What we can do is we can create a context manager around this, and I'm not going to do this in the video. I have the code over here, but I'm going to explain the logic to you and leave it as a practice activity so that you can work it out on your own. I do urge you to try this on your own before you try to look at my code. Anyway, so what you do is you enclose all of this in a function. You mark that function as a context manager because we want to create a context manager over here. Then you put all of this stuff over in the function, and this is going to be before yield because this is everything that is going on before the actual business logic. Then this one line over here, instead of this line over here, what we want to do is we want to allow other people to define their own business logic. So this is going to be the processing. So what we want to do is we want to yield this f. So we can say yield f, and essentially what this is going to do is it's going to allow us to say, so for instance, our context manager's name was temp file. So we can say with temp file as f, and if we yield f, this is going to go to the with block over there, just as we are getting this f over here. Right, so again, I do have the code over here down below, but I'm not going to explain this over here. I want to allow you the opportunity to work this out on your own because this is a very useful skill to have under your belt. So anyway, once you have this yield over here, after that you can have the finally over here, and that's the beauty of generators. You don't have to worry about maintaining the state. The generator is going to give you that for free. So please go ahead and do that. And once you have this context manager created once, you can use it whenever you want to create temporary files. In this section, we want to take a look at how we can do multiple things at once. So we are in Notebooks 09 and we're starting with multithreading. As always, let's start by looking at why we would want to do things in parallel. So we're taking a case study in which we want to download a couple of web pages. So we have a list of web pages over here, and you can imagine a scenario in which you're trying to download some data off of the internet, or you're trying to request multiple APIs and retrieve some data, and you want to do them in parallel. So we have a very popular package called requests in Python that allows you to download stuff off the internet. So you can request different web pages through this requests package. So if you don't already have it installed, and that is typically the case, you can install it using the command pip install requests. You don't have to open the terminal for this. You can do it directly from the Jupyter notebook by prefixing an exclamation mark with this command. So exclamation mark pip install requests, and that should install it for you. I already have it installed, so it's going to say requirement already satisfied, but if you don't have it, you can install it. And you can check that it's working by importing it. So import requests work fine. And then let's go ahead and define a list of the URLs that we want to retrieve. So these are my gists, And this is just for the sake of an example. So I have a couple of gists over here on GitHub that I want to download. These are publicly available, so these can be any URLs that you want to download. So let's go ahead and run that as well. So this is our time it context manager that we created in the last section. So let's import that as well, because we want to check how much time it takes to download all of these URLs, right? So let's run that. Then we have a function over here that is called getGist. It takes the URL of a gist as input, prints that it's starting the request, and then it goes ahead and retrieves that using requests.get. So you can have request.get and pass it the URL, and it will retrieve the whole page for you and save it in this variable r, and you can get the text using r.text. So all we're doing over here is we're getting the length of this web page. You might be interested in doing something more in real life, but here we're just computing the length, and then we output it, right? So that's our function. Retrieve the gist, compute the length, and print it out, right? So what we want to do is now loop over all of these gists, and we don't need this. What we want to do is we want to loop over all of these gists and simply print all done when they are all done, right? But we also want to time it. So we have a with time it context manager over here, and we are going to run that. So what this is going to do is it's going to start a request, it's going to compute the length of that, and then start another one, and then compute the length of that one, and so on and so forth, right? So all of these are about 1, 2, 3, 4, 5, 6. This takes approximately 9 seconds, right? So 9 to 10 seconds. Now the problem over here is, as you can see, when we send a request, it sends that request and then it waits for the request to go through. And as you can imagine, this is going to be slightly slow, because even if you have a very fast internet connection, it's going to take like half a second. And for that half a second, the computer is waiting, right? We have nothing to do because we don't have the page yet. So once we have that page, we can compute the length almost instantaneously. Then we start another request, and then we have to wait another half a second for the second request to go through, and so on. So while one request has been sent out, we're just waiting for the thing to come back. What we can do to speed things up is to send out all the requests together, right, at the same time, and we compute the lengths of each one as it comes along, right? So that's very common when we are using a browser. For instance, you open up a tab and you, for instance, open your email, you open up another tab and you open some social website for that, and you can keep hitting new tab and issue all the requests, and they come in parallel. So we can do something very similar using the concept of thread. The concept of thread is that when you are executing some piece of code, you might want to create a new worker and assign some task to that worker, and that worker is going to go away, perform that task, and when it's done, it is going to tell you that it has now performed that task, and then you can proceed with whatever you want to do with the output of that task, right? So that's the concept of a thread. So let's go ahead and take a look at this. So for this, we have a Python library which is called threading. So let's import that. So we have the threading library imported, and we are going to create a list of threads. So these are going to be our workers, which are going to go ahead and download the web page for us. So we have 6 gists, and we're going to create 6 threads, one for downloading each gist and computing the length, right? So the way we create a thread or a worker is we say threading.thread, and then we tell it what that thread is supposed to do, because like we said, a worker is going to do some tasks. So what is that task going to be? In our case, it is going to be the getGist function. So over here, this function getGist, and for each worker, we're going to pass it one gist, right? So we're looping over gists, and we are going to pass each worker this one gist that it's supposed to go ahead, download, compute the length of, and then print it out. We can tell this thread t to start. So this is just us defining what the worker is going to do. And then this is us telling the worker to go ahead and do that, right? So these are two separate things, defining what is supposed to be done and then telling it to start doing that thing. We also want to keep a list of all the threads, all the workers over here. And the reason is that sometimes we want to communicate with the workers. So you need to keep track of which workers you have. So we have a very simple list over here, and we append the thread or our worker to that list. So once we have created the threads for all the gists, we can go ahead and wait for them, right? So waiting essentially means, as I said, when we say t.start, this thread is going to go ahead and work in the background somehow. On the other hand, we are working on the main thread. So a main thread is always there. It's what we imagine to be the main program. So the main thread is going to go ahead and continue up until the end, and when the program ends, it's going to finish. We don't want that. We want to wait for the threads to finish before we exit our main thread. So for that, we loop over the threads and we say t.join. Joining is a terminology in threading, which means that we are going to wait until that thread finishes. So here we have told all the workers to go ahead and start doing their job. And now we loop over all of the threads and we say that we want to wait for all of them. When I say t.join on one thread, I'm going to wait over here on this t.join until that thread is done, and so on for all of the threads. So this loop is only going to finish when all the threads have finished executing their tasks. So when we do that, we have all the threads done, which means all the lengths have been computed, and then we print all done, right? So to recap, we loop over all the gists, we create one thread for the gist, tell it that it needs to execute the get gist function, pass it the gist URL so that it can go ahead and do its task. Then we go ahead and tell it to actually start performing that task, and then we keep a track of all the threads that we have created. Then once all the threads have been told to go do their jobs, we wait until all of them have come back, and then we print all done, right? So recall that this took approximately 10 seconds to run when we were doing them in series. Now we are doing them in parallel, and let's see if that helps us, right? So 2161, so about 2 seconds. So for just 6 URLs, we have gone from approximately 9 to 10 seconds to just 2 seconds. So that's a huge speed up. As you can see, when you have, for instance, 1000 URLs that you want to download for scraping, or if you're downloading some data somewhere and you have 1000 URLs, this is going to give you a huge speed up. So that's a big plus. However, there is a slight problem over here that is very visible here. So we say starting request. So this is the first thread that has output the value of its gist. So see over here, we had starting request and then got response, then starting request, got response. So this was happening in series. Here, because all the threads are working together, first thread goes ahead and prints this starting request and its own URL. But before it got a chance to print a new line, the second thread started outputting its own thing, right? So starting request, the other thing, and then starting request, another thing. So these threads are essentially overstepping on each other. So this isn't a problem over here because this does not make much difference, even if the output isn't very clean. However, there are cases in which this is going to lead to problems. And in the next video, we're going to take a look at one such case in which when you have multiple threads, they might overstep on each other and essentially lead to problems. So in the previous video, we got a hint of how different threads might overstep on each other. In this video, we are going to take a look at a concrete example of how that can lead to problems. So we are still in notebook 09, and now we are in the synchronization notebook. So let's go ahead and import threading, and let's do an experiment. So we have this variable counter over here, which is 0, and you can think of it as, for instance, your account balance. And there are people who come in and send you some money, and your counter should go up, right? So your balance should go up. And there might be many people trying to send you money because you're a very famous artist, and you want to make sure that you're receiving all the money. So we're imagining that we have 5 threads running in parallel, and each thread is going to go ahead and increment your balance 100 times, right? So by the end of the day, you should have 100 increments in 5 threads, so 500 increments total. So your counter should end up as 500, right? So 5 threads, 100 increments each, you should have 500 by the end of it, right? So let's go ahead and run this. How do we do this? We want to do this in parallel. So we go ahead and define a function f, which takes a global variable counter. So global variables, really bad thing. We're just using him here for the sake of understanding the problem. Never ever use global variables, right? So just a heads up. What we do is that this f is going to be for one thread, and we want to increment our global variable counter 100 times in this thread. So we loop over the iterations in one thread times. And what we want to do is we want to take this global variable counter and save it in a local variable v, then go to sleep for a very small time just to demonstrate that we're doing something over here. So this is just to simulate that we're doing some computation. For instance, you're calculating taxes or whatever. Then we go ahead and increment this variable v and then save this variable v back to the counter. So essentially all these 4 lines are doing is take the value of counter, increment it by 1, and then save it back, right? So incrementing it. We don't want to do it as counter plus is equal to 1 because we want to make sure that this takes a little bit of time just to demonstrate the problem. So we have this function over here, and then we want to run our experiment. Again, take the global variable counter, set it to 0, and as before, we have a list of threads. We're going to create a couple of threads, tell them to go ahead and execute F, and we're going to start them and keep track of them as well. Then we join them so that we finish only when they're all done. And then we go ahead and output the calculated value and the expected value, right? So what we expect is that we should have the value 500 by the end of our experiment, right? So let's go ahead and run this and see what happens. So we've defined the function run experiment, and then we go ahead and run this. So the calculated value is 100, but the expected value is 500. So what went wrong? We thought computers couldn't make mistakes. We obviously have a mistake over here. What is the problem? Let's go ahead and look at this. So imagine that we have this counter variable 0. So this is our global variable, and this v1 is the stuff done by thread 1, and the same stuff is done by thread 2, but we're calling them v1 and v2 for the sake of understanding. So we have this idea of taking the global variable, putting it in v1 in thread 1, then incrementing it and writing it back to the global variable. The thread 2 is doing the same thing. So take the value of counter, put it in v2, increment it, put it back in. So if we do that, we get the value of 2. So 2 increments, we get the value 2. This is what we expect. However, the problem is that you have multiple threads running at the same time. So what happens is, you have this global variable, thread 1 starts executing, and it takes the value of counter, puts it in v1 and increments it, but before it gets a chance to write it back to the counter, this thread is stopped and the other thread comes along. Or you can imagine that they're running on 2 cores, and before this thread gets to write the counter variable back, this thread gets a chance to execute on another core and tries to read the counter variable. Think of them as running in parallel, not in sequence. However, this thread over here is just slow enough that this second thread has started. It has taken the counter variable from the global value, which is still 0, saved it in v2, and then incremented it and written it back. Now the counter variable after this line is going to be 1. However, thread 1 does not know that. It has already read the value, and it has the value of 1 over here, and it's going to write that to the counter back. And we're going to get the value as 1 output. So let's go ahead and look at this in the tutorial because it's very essential that you understand this concept. So we have the counter variable over here, 0. So we have a global variable counter, which is 0. Thread 1 starts, it takes the value, and obviously it's 0. It then goes ahead and increments it. However, before it has a chance, so it has incremented this over here, before it has a chance to write it back, thread 2 gets the chance to read the value of counter again. So counter currently has 0. When v2 takes it, it's going to go as 0 over there, not as 1, even though we technically think that it should be 1, but it's not. And v2 increments it, so v2 goes to 1. Now this v2 is going to write it back to counter, so that goes over there. However, thread 1 is now getting a chance to execute its final statement, and it's not going to go ahead and look at that again because that's not how it works. Thread 1 does not know that counter's value has changed, so it has no reason to go back and look at it again. So it's going to go ahead and execute its own statement, which is counter is equal to v2, and v2 is going to go to counter, and counter essentially stays at 1, and the value that we get out is 1. Right, so that's essentially what's happening. Essentially, these two threads are trying to access the same variable at the same time, and because of that, they are getting into a race condition. And in this race condition, whoever is the last to write the value wins, and this value is essentially lost. Right, so for instance, if we had v2 is equal to 100 over here, this value is going to go in over there, but counter is going to be replaced by the thread 1 when it runs, right? So it's still going to be 1. This value is essentially going to be lost. So whatever the last value is, that's going to win, sort of. But in any case, we are going to be on the losing end. So how do we take care of this? What we do is we want to ensure that this portion over here, this gets executed at the same time. So if we can ensure that these 3 statements stay intact, we can be sure that if another thread comes along, it's going to read the updated value and not the old value. So this portion over here, these three statements, or if you go over here, these four statements over here, these are our critical section. So this is what is called a critical section, and we want to make sure that the critical section stays intact. So we can have other stuff going on and they can run in parallel, but this portion over here cannot be run in parallel, right? So that's what we want. And the way we do that is using the concept of locks. So here we go. We create a lock, and you can think of it as a physical lock. So you have a barn door and there is a lock up there. You enter that door using your key, and while you're in there, nobody else can enter. And once you leave, then somebody else can come in. So that's the idea of a lock. So we define a lock using threading.lock, and then we go ahead and redefine our function f. And here we have these two lines. So lock.acquire and lock.release. Essentially what this is saying is, if I acquire the lock, so if I'm in thread 1 and I acquire the lock and thread 2 comes along and tries to acquire the lock, it's going to wait over here until I have released the lock. So I go in there, acquire the lock, execute all of these, and then release the lock, and then thread 2 can go ahead and execute this portion over here, right? So once we redefine the function and run the experiment, now you can see that the expected value and the calculated value are the same. So recap, we have lock.acquire and lock.release, and within this we have the statements which need to be kept together to ensure that our data is not corrupted, right? As long as these four statements are executed together, we will not have a corruption in our data, right? So that's the idea. Now there are two problems in this. First problem is that you have to ensure that you understand your logic thoroughly and understand what the critical sections are. You have to understand exactly where things might go wrong, and you want to ensure that you put locks around them, right? So that's the one problem. You need to understand where critical sections are. The other problem, which is slightly smaller, is that people forget to release the locks. And if you don't release the lock, it's as if you go into the barn and you lock it and then you never unlock it, right? So that's bad. Nobody else can enter this over here, and your program is essentially going to get stuck and nothing's going to happen. So that's bad. However, that's the easy part to fix. So in Python, we have the concept of context managers, if you recall, and here we have the context manager, you can say with lock, and then within this, the lock is going to be acquired. You don't have to release it. When with exits, in its housekeeping, it's going to release the lock automatically. So that second part is taken care of. People typically tend to forget releasing the locks, so that is taken care of using the with block. However, the first problem still remains. You need to make sure that you identify the critical sections clearly. And the problem over here is you typically have to figure out which parts you don't want breaks in. So that's what the definition of a critical section is. You don't want this portion to be separated. You want all of them to be together. And that's the difficult part. It's much more common to figure out which parts you do want the thread suspended at. For instance, if you recall, in our multi-threading previous notebook, we knew that it was this guy over here, r is equal to requests.get. This was the guy that was slowing us down. So what if we had a way of not having to define our critical sections, but having a way of defining which portions we think are going to slow us down? So the threads can execute in serial, but whenever they get to a portion that can be slow, they can somehow split and do things in parallel, right? So that will make our life a lot easier. And that's touching on a slightly advanced concept. It might not be termed as intermediate, and since this course is targeted at intermediate level, if you understand the concept of synchronization up until now, that you have critical sections, you have locks around them, you should be fine. However, if you want to go to slightly higher level or expert level, if you want, you should understand the next video as well. So the next video is going to be completely optional, and there we're going to take a look at the problems that are within locks and then try to cover them using a completely new technique. So to recap this lecture, we have the idea of things running in parallel, and when they do run in parallel, they might overstep on each other and lead to data corruption. For that, what we do is we create locks around portions which are critical and which should be executed together. And the way we do that is by acquiring a lock and then releasing it around the critical section. Once we do that, we are sure that all of these four statements, which are critical and should be kept together, they will be kept together. And by using this concept of locks, we will avoid data corruption. The problem though is that you have to have a critical understanding of which portions should be kept together, but that can come with experience. Please go ahead and look at these examples in detail slowly so that you understand how different threads running together can overstep on each other, and then how we can take care of that. And please make sure that if you have any confusion, you do post them in the Q&A portion so that I can answer them. So the last topic of this section is asynchronous programming. This topic is optional in the sense that to fully understand it, you would have to spend quite a lot of time with it. But it also follows very logically from the topics of multithreading and synchronization using locks that we've been covering. What's more, it's a growing trend, and as you can see from the trend line over here, it has been growing continuously for quite a while now. And in recent times, because of Python 3.6 built-in support for asynchronous programming and the fact that the same syntax is used in modern JavaScript as well, lead to immense popularity of this type of programming, and you're bound to come across it sooner or later. So it's best if you understand it in this context at the moment. The basics of the concept are very simple, and we're going to cover them in a couple of minutes here. So we are in notebook 09, and we started with multithreading, and you would recall that we had this task of downloading a gist, and we passed it some URL and it was downloading it. The problem was in this line over here, which was a very slow task, and we were waiting for the page to come back over the internet, which was a slow task. So that was what we had, and because of that we created threads, and in threads later in synchronization we saw that we might have a problem in which there might be a critical section, and we would have to identify that critical section to ensure that we acquire and release our locks around it. And we left off last time by mentioning that it's much more difficult to figure out what critical sections are. What if we were able to make everything critical, which would mean that everything would be running sequentially except the things that were slow? So what if we could make everything sequential except this one line over here? That would make a lot of sense, because it would get rid of the problem of waiting for the slow processes to go through while keeping everything else very clean, right? That is the whole idea behind asynchronous programming. So now we are in async.ipynb in the same notebook/09. So we are in async.ipynb, and what we want to do is we want to start with the same use case again. So if you recall over here in multithreading, we installed the requests package, which would allow us to request URLs. So in asynchronous programming, we have to start with AIO HTTP, and we'll see why this is in a minute. But let's go ahead and install this. So I've already installed this, so it's going to say requirement already satisfied. For you, it might go ahead and install it. Now, we have the same list of gists that we want to download. We want to import AsyncIO, which is the package which handles asynchronous programming in Python. We have the package AsyncIO, which will be available if you are running Python 3.6 as suggested in this course. We also want to import AIO HTTP. Again, we'll see why this is in a minute. Then we have this getGist function over here, which is essentially the same function that we had over here in this multithreading code. Right? So essentially the same idea. Print that we're trying to get this URL, which is going to be the gist. Then the way AIO HTTP package works is it creates a session. So we're going to say with AIO HTTP.client session as session. So this is exactly the same as with open file name as F, right? So we have a context manager which creates a session for us. And because this is a context manager, it's going to make sure that it closes the session and everything else that a context manager is responsible for. In the next line, we have this session.getURL as response. So this is the way AIO HTTP works. You give the URL to the session object and it returns a response. So again, this is in a context manager. So we have with over here, and within this block over here, we are bound to have a response. And you will remember that this response.text was our culprit, right? So this is the portion that is the actual slow part. What this does is it goes ahead and fetches the URL and the body of the HTML page. Now this is our culprit over here. What we want to do in asynchronous programming is identify the culprits and put a keyword over here, which is await. Right? So how this works is not important at the moment. What's important is that we are marking explicitly the portions which we think are going to take time. So this is the change of paradigm of programming. Now, instead of locking critical regions, you are providing information to the programming language about which portions you expect to be slow, and everything else is going to run sequentially. So the whole idea of asynchronous programming is you are going to mark the portions of your code which you think are going to be slow and which are going to be blocking. So what's going to happen is when the interpreter gets to response.txt, it's going to await for it. And what that means is that while response.txt is running, the control is going to be passed to some other function which is going to run. And what that means is while response.txt is running, control can be passed to some other function. You will see how this works out when we finish this whole thing. Now, because we have this await keyword over here, it means we're doing asynchronous programming. And because of that, we have to define this function as async. So we have two new keywords, await and async. And that is why sometimes this type of programming is called async await type of programming. So what we have is a function that might be slow. And because of that, we want to create asynchronous programming. So we put await over here and we define this function as async. Because the creation of the client session might also be a slow process, we want to allow this thing to be run asynchronously. And for that, we have the idea of asynchronous context managers. And in order to define that, we have another keyword which is called async with. So you don't have to understand what that does. What this means is that within this context manager, there might be an await. Similarly over here in this session.get URL as response, this can also have some await in it, and we're going to define that as async as well. To recap, we have taken this response.txt and we have defined that we need to await for this, right? That's the idea. We want to await until response.txt comes back. And because we are waiting for something over here, we have to define this function as asynchronous. And because these two functions can also have awaits in them, we have to put them in async with instead of just with. So we define this function using this way. So as you can see, the logic of the function is essentially the same. We have only made very few minor changes over here. So we have await, async, async, and async, and the whole logic is remaining the same. So this leads to our function looking like this, right? So we have this over here. So this defines the function as being asynchronous. These two are asynchronous context managers. And then we have await over here. Then we compute the length of the page, and then we print it out and return the length. So this is our getGist function over here. Now, because this is an asynchronous function, it cannot be simply called from the main thread. What we're going to do instead is we're going to set up an asynchronous event loop. Think of this as the driver that runs your whole asynchronous programming. And this is why you have to think of asynchronous programming from a different perspective. So what happens is you have an event loop. So this is the driver who is sitting there, and you give it tasks and it's going to run those tasks for you. So we create a new AsyncIO.new event loop and set this as our current loop. So this is going to be the driver that is going to run. And we get an instance of this back. So loop is equal to AsyncIO.get event loop. So this loop guy over here is the code responsible for running our tasks. So we have the driver. Now let's create some tasks. So we want to download all of the gists. So each gist downloading is going to be one task. So we loop over the gists, and in this we are going to have one G, which is going to be one gist. So what we want to do is we want to call this asynchronous function getGist. But what's important over here is that when we say getGist G, this is not going to call the function. Because this is an asynchronous function, we're just telling it that this function will need to be available in the future. Just as over here in threads, we said threading.thread, and then we told it which function would need to be run when the thread is run. And then it was run when we said t.start. So similar concept over here. Here we are just saying that sometime in the future, when we tell you to run, you should run this asynchronous function and ensure that its result has come back. So that is called a future. In asynchronous programming, the result of an asynchronous function is called a future because it's not available right now. It's going to be available in the future. So we have this future, and just for future reference, because we might want to use the results of this future, we append this in our list, right? So this line over here and this line over here is just for housekeeping, and this is the guy which is going to run the task, right? So let's go ahead and run this. But we haven't started running it at the moment. As you can see, nothing has happened. We are just compiling a list of things that we want to do. Once we are done with that list, what we can do is we can say loop.run until complete. So run all the tasks that are available. And then we can say AsyncIO.wait tasks. So what wait does is it waits until all the futures for all of these tasks are available. And loop.run until complete essentially compiles them all together, right? So that's the whole idea of this thing over here. And we time it using our %time magic command. So we run this, and when we say loop.run until complete, this is going to go ahead and run all of the tasks for us. And as you can see, it started the gets all immediately, and it printed out the results as they came back. And once we're done, we are given all of the finished tasks back as well. So for housekeeping, we're going to say loop.close. And if you recall over here, we saved all the futures in our tasks list. So what we can do now is we can say tasks0.result, and this is going to have the length that was returned by this function over here. So if you recall, glength was returned by getGists, and this is going to be saved in the result function of the future. So task0 returns the future for the first gist, and .result gives us back whatever was returned by this function over here. So to put everything together, we have taken a look at one way of doing asynchronous programming, and that is the idea of AsyncIO. We started with a package which is AIO HTTP, which is essentially asynchronous IO HTTP requests. So this package allows you to do asynchronous requests to HTTP protocols, and we put an await keyword over here that meant that we are going to wait for response.txt. And because of that, we defined this function as asynchronous. Asynchronous functions run in an event loop. So we created an event loop. We compiled the list of tasks that had to be completed by this event loop, and then we ran this event loop. When we ran this, all the tasks were executed almost synchronously, and these tasks were executed in parallel, kind of. The way this works is the event loop starts, it takes a task, it executes it sequentially, but when it gets to the await, it puts this on hold and goes back to another task and executes that. And when it gets to the await of that task, it tries to execute yet another task. When the response comes back, this thread is also put back onto the queue, and then it's executed from this next line onwards. If you recall the idea of generators, that's essentially what the generator was doing as well. It stopped executing at some point when there was a yield, and at a later stage, that function could continue executing from that same point in time. And under the hood, Python uses generators to implement this whole thing, but you don't have to understand that at the moment. But it's the same idea. So the benefit now of this is you can write functions which look like they are running in sequential form, except they can run in parallel and concurrently, saving you time, giving you all the benefits of threads without making you implement the ideas of locks and ensuring synchronization, which is very difficult to do. In the previous section, we took a look at a different type of programming, which was asynchronous programming. Here we want to take this a step further and take a look at yet another paradigm of programming, which is called functional programming. So we are in notebook/10. So functional programming is a different paradigm of programming. Think of it as being a parallel to structured programming or object-oriented programming. So the idea is to treat all computations as mathematical functions. It means that all procedures are going to be manipulating your data structures, and there are going to be no side effects, right? So it's not going to be doing anything that is other than manipulating the inputs to produce outputs, right? So that's a little difficult to understand, but the whole idea is that you can predict the outputs given the inputs. It's not going to take into consideration anything other than the inputs when computing the outputs. So why is that useful? It's useful because it makes it much more easy to debug programs. So if you have a function and you can define its input, for instance, you can write test cases for it, as we saw earlier in the course. You can predict what the outputs are going to be, and it makes it really easy to debug and to find out when there is a problem and where it is, right? They're also a lot easier to parallelize. And the reason is that a function is going to depend only on its inputs, and therefore if you have 1000 invocations of the same function and you can pass it different inputs for different invocations, you can run them on separate computers or separate threads or separate cores, and they're not going to depend on each other. Right, so that's a general overview of functional programming, and I know it's not very easy to understand what functional programming is. I've put a link to this really great article on codenewbie.org. I'm not affiliated, but I just found it a really good example of the difference between object-oriented programming and functional programming. So you can read through this. This is in Ruby, but it should be really easy to understand. Here, we don't want to dive deep into functional programming. We have 3 operations in functional programming that are very useful even if you are coming from an object-oriented programming background. So they're going to be useful even if you do everything else as your typical workflow, but incorporate these in your existing architectures. So the first one of these three is called map. So let's begin by taking a look at what map is. So if you recall, in Python, we have this idea of a list comprehension in which you can loop over some list and perform some operation on each item and collect them as the final results. So this is going to loop over 1, 4, 9, and 16, and it's going to calculate the square root of all of these. So obviously we need to import the square root function, and then let's run this. So you can say 1.0, 2.0, 3.0, and 4.0. So you take each element from the list, put it in a variable, apply the operation that is over here on this item, and then collect it over here. So 1, 2, 3, and 4. So that's the idea of a map. What it does is it applies a unary function, so a function that takes in just one item as input, and then it applies some operation to that. So take this item from the list 1, apply the unary function to it, and then collect the item. So that's what map does. So let's go ahead and try to do the same thing using a map. So what we're going to say is map the square root function over this collection, right? So when we do that, we get a map object back. So this is very similar to a generator that we saw earlier. And what we can do is save it in a variable and then convert it to a list to see what it's actually computing. So 1, 2, 3, and 4. So the idea is the same. The difference now is that this square root of I, this was going to be run sequentially, one element at a time. However, with map, we have the ability to parallelize it, right? So we'll come to that in a minute. Let's go ahead and define map ourselves so that we know what it's doing. So I'm defining a function mymap over here that takes a function as input and a sequence over which this function is going to be applied. So if you recall, this mymap function is taking another function as input, therefore it's a higher order function. So you can go back and review the higher order function videos if you don't recall that correctly. Anyway, so we're computing a list which is going to be the result. For each element in this sequence, we are going to compute the resulting value of f as being applied on this element, and then we're going to append it to our result. And finally, we're going to return the result. So if you do that and you call mymap with the square root function and pass this as the sequence, this is going to do the same thing as this map over here, right? Once we have an understanding of that, as we did in higher order functions video, we can go ahead and define a new function over here. For instance, the power of 2, which takes one element k as input, because this has to be a unary function, and it computes the kth power of 2 as a result, right? So if we say power of 2, 3, this is going to be 2 raised to the power 3, which is going to be 8. So what we can do is we can map this power of 2 over all of these elements, and what it's going to do is it's going to compute 2, 4, 8, and 16. So 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and 2 raised to the power 4. We can also shorten this by removing this function name over here and replacing it with an anonymous function, lambda, right? So again, we covered this in higher order functions video. So if you don't recall this, you can go back and take a look. Essentially what lambda k is doing is that it's defining a function that takes one input and computes this result over here. So now we have the ability to take a sequence, apply some operation to each of its elements, and then save the result as another list, right? So let's run this. So 2, 4, 8, 16, the same idea. It's a very simple operation. I spent a lot of time on it just so that it's clear to you. However, the operation itself is very simple. This is all there is to it. However, by the end of this section, we'll see that this simple operation combined with a couple of other things leads to a completely different paradigm of programming, which has been gaining traction for a long while now. So that was one of the three operations that we want to see from functional programming. In the next video, we're going to take a look at the other two. So having taken a look at map, let's go ahead and look at another operation which is called filter. So what filter does is, again, it takes a sequence and it applies a Boolean function onto it. Whichever element of the sequence satisfies this condition, so returns true as a result of this function's application, that is collected and all the others are ignored. So for instance, we apply filter on this sequence and pass it the function str.isAlpha. What isAlpha does is it returns true for alphabets and false for everything else. So it's going to take x, send it to isAlpha is going to return true, it's going to collect this, and so on until it gets to 2. When it gets to 2, it passes it to isAlpha and that's going to return false, and that is not going to be collected in our final list. So let's go ahead and run this. This x is now a filter object, again a type of a generator, and if we convert it to a list, we get x, y, and a. So we have two things now. We can apply a single function to all of the elements through map and collect the results. We can filter some values out by passing them through filter and giving it a Boolean function. So any element that gets false as a result of this function's application, that is omitted, everything else is kept. So we have filter and map. The final thing that we want to do is reduce. So reduce isn't a built-in function. We have to import it from functools. So let's go ahead and do that. And again, let's do it with a case study. So what reduce does is it applies sequentially a function on two elements and returns some value as a result, right? So for instance, we have a function over here, add, which takes x and y, two values, and returns their sum, right? So let's go ahead and run this, and then reduce add 1, 2, and 3, starting with the value 0. So what reduce is going to do is it's going to take this starting value 0 and then this first value over here 1. 0 and 1 are going to be passed to this function add, and whatever the result comes out, that intermediate result is going to be used to invoke add again. So this intermediate result is going to be the first parameter of the second invocation of this function, and the second parameter is going to be the second element over here, right? So essentially reduce is going to do 0 plus 1, it gets 1. So then it's going to do 1 plus 2, it gets 3. Then it's going to do 3 plus 3, and it's going to get 6, right? So the final result is going to be 6. Right, so let's go ahead and change this to 4 and change this to 10 so that you can understand better. So what reduce is going to do is take 0 plus 1, it gets 1. So 1 plus 10, it gets 11. 11 plus 4, it should get 15. So that's going to be the operation of reduce. As you can see, all three of these operations are very simple. Why are they important? How do they lead to a lot more power? Let's go ahead and take a look at an example for that. So for instance, you have a couple of million files, and in them you have some strings, and what you want to do is you want to count the number of occurrences of each word, right? So a word count. So let's go ahead and do this. That's our objective, counting words in all of these lines all combined together. So we need 1, 2, and 3 for cow. We need 1 and 2 for a, capital A, 1, 2, and 3. We need 1, 2, and 3 for is, and so on, right? So that's the count we're looking for, all lines combined. So let's go ahead and first define a function which is count words that takes just one string. See over here we have a list of strings, but we are writing a function that can only perform the counting on one string, right? So this is a function that takes in one string and computes the number of occurrences for each word. First we define a default dictionary, right? So this is very similar to a dictionary that you would be familiar with in Python. However, what it does is if you try to give it a key that does not exist previously, it's going to initialize it with a default integer value, which is 0, right? So let's take a look at an example and we'll see what this does. So what we're going to do is we're going to split the string on spaces, and then for each word that we get as a result of that split, we're going to say counts word plus is equal to 1. So for instance, here we are going to have a cow is. So for the first invocation of this iteration, we're going to get capital A in word, and we're going to say counts capital A plus is equal to 1. So plus is equal to 1 would mean counts word plus 1, right? So that's what it means. However, counts word does not exist. Counts of capital A word is going to give us a key error if this was a normal dictionary. However, because this is a default dictionary, what default dictionary does is it assigns a value 0 to it if it's not found. So instead of a key error, you get 0 out of it. So 0 plus 1 is going to be 1. So what this means is we are going to have defaults initialized to 1. This helps us get rid of the extra try catch or an if in which you check whether the word key already exists in the dictionary or not. So that's default dictionary. You can go ahead and take a look at this collections package, which has other stuff as well. So default dict is over here. It explains what it does. It's a very useful tool to have under your tool belt, and you would use it a lot once you get to know it. Anyway, so let's get back. So what our function is doing is it's splitting the words from the string, and it's incrementing the count for all of them each time it sees them. And finally, it returns the counts default dictionary and converts it to a dictionary, a normal dictionary, before sending it, because we want to work with dictionaries and not default dictionaries. Anyway, so that's our function. Essentially what it does is counts the word in one string. So if we say count words line 0, it's going to return A is occurring 2 times, small a 2 times, animal twice, and so on and so forth, right? So there's a dot over here. We don't really care about that at the moment. Anyway, now that we have this function, what we can do is we can take this list of lines and map the countwords function onto it. And what this is going to do is it's going to return us two instances, two dictionaries. So this one is for the first line and the second one is for the second line. But they're separate from each other because map does not combine them at all. So we have this a over here. In the first line, we have two a's. In the second, we have one a, and so on. So what we can do is we can save this in a variable. So counts map is going to go into a variable. So map is done. Remember, what we're trying to do is we're trying to count words for all the lines, right? And these are not yet combined. So a should give us the value 3, not 2. So what we're going to do is we're going to do a reduce counts function. What it's going to do is it's going to take two dictionaries and it's going to somehow merge them together, right? So let's run this just to see what reduce is passing it. So we take counts map, we pass it to reduce counts, and for the initial value, we give it an empty list, right? So let's run this and you will see that reduce is getting two values over here. So first time it's getting the empty list. So this is coming in from over here. And for y, it's passing it the first element of the counts map. The second time it's using the returned value of the first invocation as the x value, and the second value is going to come from the second value of counts map. So please go back and take a look at this in detail so that you're sure what it's working with. Now let's go ahead and actually define our reduce counts function. So the way reduce count work is it's going to initialize a counter. So a counter is essentially a dictionary which has keys and values, where values are going to be the counts, right? So we're going to have a initialized at 0, cow initialized at 0, and so on and so forth. And while we can do this with a dictionary as well, counter is very useful because you can simply go ahead and say counter.update x, and it's going to simply take all the numbers from x and increment them. And you can say counter.update y, and it's going to take the values from y dictionary and update those as well. So let's go ahead and take a look at an example for this. What we're doing is we're initializing a counter, taking the values from x, updating them in our counter, taking the values from y, updating them in our counter, and finally returning the dictionary, right? So let's go ahead and do this. And then do the same thing. Start with an empty dictionary, use the counts map to subsequently pass stuff to reduce counts using the reduce, and then finally convert it to a dictionary. So because we're returning dictionary from over here, we don't really need this dict. So let's get rid of that and let's run this. So now you can see that it has combined both of them together. So let's go ahead and look at this to understand what's happening. So what reduce does is it takes the empty list and this first list over here, passes it to reduce counts. X gets the value of empty list and y is this guy over here. Then what it does is it initializes the counter, says counter.update x, because x is an empty list, it doesn't do anything. Then it says counter.update y, and what this is going to do is in this counter, it's going to take all of these keys and it's going to set them as the value. And it's going to return this list. So it's essentially returning this list over here. The second time reduce calls it, what it does is it takes this value and puts this as x, and it takes this second value over here and puts this as y. Then we initialize another counter and we update x. So all of these values, a2, cow2, etc., get initialized in this counter. And then when we say counter.update y, what it does is it goes ahead over here and sees that capital A has value 1. So it increments the 2 to create a 3 out of it. So similarly, all the different words are also incremented as much as different dictionaries. So if you have multiple lines over here, reduce is going to apply them multiple times and it's going to ensure that you get the actual correct count out of it. So let's go ahead and create a new line over here. So let's say another cow. Okay. So the same functions applies. We need to create a new counts map. So let's run this again so that we can see what's happening. So we have this result for the first list, this result for the second list, and this result for the third list. Then we can say counts map and reduce counts, and you can see that it's returning everything over here just as it should. So at the end, reduce is only going to return one list, and that's going to have all our word counts. So back to our original question. What's the point? The point is that it's extremely easy now to parallelize this. Imagine that you have a scenario where you have 1 billion files and a Hadoop cluster of 5,000 machines. So Hadoop is essentially a framework that takes the idea of map reduce and tries to parallelize the mapping and the reduction. So you can take a million files and pass to one machine. Since there is no dependency between different invocations of the map, it's going to compute all of these on separate machines completely independently. So while you're computing this, another machine can compute this guy over here. And then you can go ahead and do the reduction operation in one quick step. So this is going to lead to almost 5,000 times speed up. And if you have more threads on one machine, each thread can run independently. You don't have to worry about locks and everything. And you don't have to worry about asynchronous programming. You don't have to do any of that. You get everything for free as long as you understand how the MapReduce paradigm works. So this has been a dense video. Please go back and take a look at it again to make sure you understand it. The operations themselves are very simple. It's their combined power that takes a little bit of time to sink into. I'm sure you've heard of Hadoop and Spark. They are extremely important for big data processing in large organizations which produce data on the order of petabytes. So simply by taking the concept of map and reduce, people have come up with the idea of massively parallel processing of big data. And Hadoop and Spark are two of the most popular frameworks for that. So the whole idea is you use map and reduce and a couple of other things to program your code, your problems in a slightly different paradigm. And once you have that, Hadoop or Spark can take your problem, take your code and parallelize them in massively large clusters. For instance, 5,000 machines, 10,000 machines, they're very common. So if you want to explore this further, you can take a look at this link over here, which is a tutorial on getting started with Hadoop. And for Spark, you can go to the official document over here. So again, this has been a dense video and it's something that's very useful to have under your tool belt. It's going to open up a different type of paradigm for you to program in. And it's one of those things that you have to learn if you want to go from beginner level programmer to an advanced level programmer. Have fun. Let's do something a little less dense and a little more fun. So we are in notebook/11 and we're looking at the topic of plotting. So this is a very important topic and you'll come across it definitely if you're working with data science or machine learning. You will come across it if you are creating web backends and admin panels and you have to show statistics for anything. You will come across it if you're doing scientific computing. You will have to use it if you are doing research. In short, it's something that you're definitely going to come across and it's very easy. Unfortunately, many people aren't even aware of this tool and the fact that it's extremely easy. If they did, a lot more people would be using it. So that's the goal. We want to show you how to create plots. Now we're going to use a very basic package that's going to give you the understanding of how this stuff works. Once you're familiar with this, you can go ahead and do a lot more interactive plots, stuff that can really take advantage of the strengths of Python. Anyway, let's start with the basics. So first, what we're going to do is we're going to import a package called NumPy or NumPy. What we're going to do is we're going to import it as NP, right? So import NumPy as NP, and that's by convention. And that's another thing that we want to emphasize over here. Many times you're going to see that people import certain packages as a shortcut, right? So they're going to use the as keyword. And whenever you do, please make sure that you follow that convention because one, the conventions are there for a reason. And two, if you use those conventions, you're going to be a lot more comfortable working with codes provided by other people, right? So for instance, NumPy is going to be almost always imported as NP. So you can probably shorten it to N, but that's not a good idea. Anyway, let's go ahead and use this. So what is NumPy? NumPy is a numeric computation library for Python. It's extremely optimized for doing stuff like vector manipulation, matrix multiplications, and all of those operations that come from linear algebra. It's the foundation for a lot of data science and machine learning that goes on in the Python ecosystem. And it's a really good package to understand. Here, we're just using it to create a vector, which is going to go from 0 to 10 in 40 steps. So let's go ahead and create this. This is through the np.linearspace function. Let's go ahead and run this. And you can see that we are going from 0 to 10 in 40 steps, right? So that is a one-dimensional vector. We're not going into the details of what vectors are and how they are implemented in NumPy and what the nuances are. We just want to use them for now. So the type of X, as you can see, it looks like a list, but it's slightly different even in visual representation because it does not have commas in between the elements. And if you do type of x, it's a numpy.nd array, so n dimensional array where the dimension over here is 1. Once you have this nd array, what you can do is you can go ahead and perform operations on this array, and it's going to be extremely optimized. For instance, you can compute the cosines of all of these values, right? So for that, all you have to do is np.cos and pass it the nd array and save the resultant in C. So if you do that, these are the cosine values. Again, we're not really interested in the semantics of what cosine is. All we want to do right now is to plot it. And for that, we're going to use the very popular library called matplotlib. There are many ways that are around in the ecosystem for importing matplotlib. The one that I prefer is import matplotlib.pyplot as plt. You can also have import pyplot as plt and a lot of others. And that's the other reason why conventions are good. If you use as plt, all the codes are going to work whether you import pyplot, matplotlib.pyplot, or any other variation of this. So matplotlib is the foundation of all plotting in Python, and there are many other libraries which are slightly more powerful, more interactive, but if you understand matplotlib, all of the other ones should be really easy to work with. So let's go ahead and import this. Now matplotlib can generate figures for you, and typically when matplotlib generates some figures for you, it opens up a new window. And because we are working in the Jupyter notebook, we don't have the option of creating windows. We're in the browser. So what we want to do is we want to tell the Jupyter notebook to capture those figures and display them inline within our Jupyter notebook. For that, we have a magic command, %matplotlib inline. So this is only needed if you're working with Jupyter notebook. If you're working with a script, you don't need this. Anyway, since we are in the Jupyter notebook, let's go ahead and run this as well. Now what we want to do is we want to create a plot in which the x-axis is going to be this guy over here, our variable x, and the y-axis is going to be this variable c. So for that, all we have to do is issue a command plt, which is from over here, .plot, give it two arguments. The first is going to be the x-axis values and the second is going to be the y-axis values. This is going to return an object to us, and what we want to do is we want to make sure that it's not displayed in the outline over here. We don't want to display the object here. We just want to have the plot displayed to us. So what we do is we say underscore is equal to, and it's yet another convention, which means that the result of this function is going to go into a variable, and we're not really interested in actually accessing the variable later on. So you would see this around in other people's code, so you need to understand what this means. Essentially, it means is ignore the result. We don't care, right? So let's go ahead and run this. As you can see, by just this one simple command, we have created a fairly nice looking plot, which is showing our x-axis and y-axis over here. Now we can go ahead and do slightly more complicated stuff. So let's go ahead and save the sign of the original values in S. So these are our sign values, and then we can go ahead and create a figure. So if you want to plot multiple trends or multiple lines on the same figure, you have to issue the plt.figure command over here. So what this is going to do is essentially it's going to create one figure, and every plot command later on is going to go into this figure. So let's go ahead and run this. So as you can see, we are getting this output over here, and if we don't need that, we can say underscore is equal to, and that goes away. So essentially that's what underscore does. It's not really important. So we have this plot over here for the cosine and sine, but how do we know which one is which? For that, what we're going to do is we're going to add a legend to it, and we're going to assign labels to these lines. So let's go ahead and create a new figure, plt.figure, and then we are going to do two plots, the x-axis and y-axis values, and we are also going to pass it a label. So the first one is cos and the second one is sine. We also want to assign a label to the x-axis over here, and that is going to be x, and to the y-axis, which is going to be sine x or cos x. And we want to display the legend as well. So let's run this and see what this means. So we have this guy over here. This box over here is our legend. We have the x-axis label and the y-axis label, and everything is a lot more clear now. So instead of this guy over here, we want this. So just a side note, whenever you're doing plots, you want to make sure that you have the labels for the x-axis, the y-axis, and all the different series that you are plotting over here. So in the next video, we're going to take a case study and plot the time taken by two variations of our Fibonacci function. For this case study of plotting, what we want to do is we want to take two algorithms for calculating the Fibonacci number and then find out how fast one is relative to the other. So here are our two variations. One is called fib slow because we know it's slow, and the other is called fib fast because it's a faster one. We want to find out just how slow this first one is, right? So this first one is our older algorithm, so the one that we saw earlier on, and the second one is a dynamic programming algorithm. You don't have to understand how this algorithm works. Essentially what it does is it goes ahead and builds the series step by step so that it does not have this recursive call in it, but you don't have to understand how this works. If you want to understand this, please do post a question in the Q&A part and I'll try to answer this. But for now, it's sufficient to understand that these are two different ways of calculating the same thing. So what we want to do is we want to execute this and then create another function. So this function is going to be a higher order function, and what it's going to do is take in a function as input, and it's going to take a range as input. So this fn is going to be a function that is going to calculate the Fibonacci number. We're taking this as a variable over here because we want to be able to pass fib fast or fib slow to this time function. What it's going to do is it's going to loop over this range. So let's say we tell it to go from 0 to 30, and it's going to loop over this, and it's going to calculate the Fibonacci of 0 and then of 1 and then of 2 up to 30. And we're not interested in the result, so that's the underscore. What we are interested in is in the time taken by the function to calculate the Fibonacci number for this particular value, right? So Fibonacci of 0 is going to be very fast, for 1 it's going to be slightly slower, and for 30 it's going to be quite a lot slower. We want to figure out just how slow this is, and that is going to be saved in this time taken. And then we keep track of the different times in this times list, and then at the end return the times list. So in summary, time function executes the function that is passed to it over a range of values and calculates the time taken by the function for these different values. So let's run this and it would become a lot more clear. So our range is going to be from 1 to 30, and what we're going to do is we're going to call time function on fib slow with the same range, and then we're going to call the same function for fib fast over the same range, and we're going to save both of these times. So let's run this, and you can see that the slow one starts off with 10 and goes up to 442,000, and the second one kind of stays at 234. But just by looking at the values, we cannot really see the trend in the growth of the times, right? So what we want to do is we want to plot both of these lists. So this is fairly simple. Let's go ahead and import the matplotlib.pyplot and then create a figure, plot the values in which the x-axis is the range and the y-axis is the time taken by the slow Fibonacci algorithm, and then plot another one in which we plot the same x-axis, and for y-axis we have the fib fast times, and we give them the appropriate labels, and we give the x label as n, which is the value for which we're computing the Fibonacci, and the y label, which is the time taken by the function to compute that value. And finally we have a legend which shows us the labels. So let's go ahead and run that, and now you can see that the slow fib is increasing exponentially. So if I go to like from 30 to 35, it's going to be a huge number, whereas the fast fib algorithm is essentially constant. It is increasing, but it's increasing at such a slow pace that even if we go up to 1,000, it's still going to work fine. This visual representation gives us an understanding of just how these two algorithms are different from each other. So that was our case study. We took two functions and we computed their times and then plotted them. What you can imagine is that you can come up with different types of lists for different types of operations and then plot them to visually analyze your data. And this is a very powerful tool to have under your belt for a variety of domains. In this section of the course, we want to take a look at yet another very important tool that is not specific to Python. You can find it in many languages. Almost all modern languages have this tool available. And it's one of those things that's an extremely useful tool, and you're going to come across it if you work professionally with almost any type of work. So we are in notebook/12, and the notebook is regularexpressions.ipynb. Let's start with what we're trying to do. So we have some string over here. So it's a long, complicated string, and what we're interested in is extracting the email that is present within this string. Now, if you are a beginning level programmer, you might be thinking, well, I can look at this length and extract the substring starting from this location going up until the space. But the problem is that this string might change in length. It's extremely unstructured. You're not sure what is going to come up in this part of the string, and you're not sure what the email looks like. There are a lot of complications. So if you try to do this with an if-else type of a structure, it's going to be extremely difficult. So we use what is called a regular expression, and we try to extract it using that. And you will see that this becomes very easy once you understand the idea of regular expressions. Now that is our end goal. However, let's start small by explaining what regular expressions are and how they work. So let's take a simpler example. So we have this string over here. Let's call this haystack. And it's a simple string. It says date : 03/02/2025. And we call it a haystack because we're going to try and find a needle within this haystack. Right, so let's run this. Our needle is DA. So this is the pattern that we're trying to find within this string. And as you can see, this DA is present immediately at the beginning of the string. But we're going to make it a lot more complicated after a little while. So let's run this. So we have two things. We have our haystack and we have our needle, and we're trying to use the regular expression package, which is RE in Python. In any other language, you might have another package, but almost all languages are going to have a package available for regular expressions with almost the same semantics as Python. So we import this package and then we say re.match. So try to match this pattern needle on this haystack, right? So we're trying to find this needle in this haystack. re.match needle comma haystack, and as you can see, it returns an object. So it's a match object. If this needle is not found in the haystack, then it's going to return none. So what we want to do is we want to save this object into a variable. So let's say match is equal to re.match, and then if we want to see what matched, what part of the actual haystack matched this pattern, we say match.group0. We'll see why we have this syntax over here in a little while, but that's how this works. So DA matched in this string over here. You might be thinking, what's the use case over here? I tried to find it and it could have just said, yes, I found it. Why is it returning it? The reason is that you can now define patterns. For instance, you can say that I am looking for a string over here, which has 2 digits. So for a digit, you can say /d. What /d means is try to find a digit in this haystack. So what we're going to say is date : and /d, and what this is going to say is it's going to go ahead and find it. And what we can do is we can say print res.group0. And what is this res? Let's extract this match object over here and say res is equal to re.match. So this is going to do the matching. And if res is found, so if the match occurred, we're going to output it. So as you can see, it is now outputting date : 0 because we have /d over here, and /d means that we are trying to look for any digit. So it can be any digit. Here it just happens to be a 0. So the pattern is now different from what was found. We can also say another digit. So now it's finding 2 digits over here. So let's go ahead and make this a little more complicated. So we have 5 characters over here. We want to add the flexibility that they don't have to be exactly date : space. It can be any 5 characters and then 2 digits. So any character in regular expressions is a dot. So we say dot, 3 dots, 2 more dots. So that's 5 characters and then a dot for a space, right? So a dot matches anything. Just as /d matches any digit, a dot matches anything at all, right? So if we say needle is equal to this guy over here and the same idea over here. So we are going to repeat this pattern again and again. Define a haystack, define a needle, do the matching. If the match is found, print it out, right? So if we do that, we are matching this guy over here. We can also say that because this dot represents a space and we are looking specifically for a space, not anything. A dot currently means anything, but we're looking specifically for a space over here. We can change this to /s. So now we have 5 dots for any 5 characters, then a space, and then 2 digits. So if we run that, we get date : 03 out. So if we change this /s to, let's say, /d, this is not going to match because after 5 characters, we have a space and not a digit, right? So make sure you run this with me because this is going to get very complicated very quickly. Let's simplify the syntax a little bit. We have 5 dots over here. So instead of having to write 5 dots all separately, we can simply go ahead and say dot, and then in braces, we can put 5. So this dot brace 5 brace is equivalent to putting 5 dots over here, right? So exactly the same thing. Then we have 2 /d's over here. So /d brace 2. So that matches the same thing again, right? We are trying to add more syntax and we're trying to simplify it as well. We can also say that I'm not sure how many characters are going to be there, right? But there are going to be some characters initially, and then there are going to be 2 digits. So in order to do that, we can say dot and static. Static means that whatever I put before the static can occur as many times as it likes. And then I want to have 2 digits, right? So this pattern says anything, any number of times, and then 2 digits, right? So if we match that, you will notice that it is matching something different now. What I expected was that I would get date colon 03, because our haystack over here is date colon 0302 2025. So this would be my anything, and then this would be 2 characters. But the idea here is that when you put star, it's going to mean anything, and it's going to gobble up anything that still satisfies the 2 digits portion over here. So this dot static is eating up until this 20 over here, and then you have 2 digits. So even though you meant something else, but this pattern matches this guy over here, so that's the result you got. This is very important to notice over here, and this is the subtlety in regular expressions that you have to understand. Regular expressions are greedy. Everything, every pattern that you define is going to match up as much as it can. If you want to get rid of that behavior and you want to say, don't be greedy, only eat as much as is necessary. So you put dot static question mark. So that's a syntax that is slightly out of the ordinary even in regular expression terms. But what this means is, here's how to read this. Any character can occur any number of times, but don't be greedy about it, right? So as soon as you can find a/d twice, this dot static is going to end its effect. So when we do that, this is going to say date colon 03. So date colon space, that is going to go with dot static, and then /d2 is going to be this guy over here. You hardly see this around, but I wanted to make sure that you have seen this just in case you come across it. But as you can imagine, this is already getting pretty complicated. And the reason is that we're trying to put the whole pattern that we're trying to find out in this guy over here, in one needle. What we can do is we can make them modular, just as we break down a whole large program into much smaller functions so that it's easier for us to understand this. So what we're going to do in the next video is we're going to break down this pattern into its 2 portions, pieces that are easier to understand right now, and 2 months later when you come back and try to understand what you were thinking 2 months back. So we'll do that in the next video. The problem that we left off on last time is that the regular expression is already getting too complicated, even though it's looking for something really simple. And the reason for this problem is that we're trying to do everything at the same time in one string over here. So we have this needle which is trying to find everything. We need to break this down into its modular structure so that it becomes a lot more manageable. So let's go ahead and do this. So we realize that in our regular expression, we have 2 parts. One is looking for some prefix which is date colon space, and then we have something that is looking for 2 digits. So this first portion over here is str date. So we break these down into 2 strings. One is going to be the part that looks for the date, and the other is going to be the part that looks for the day of the month. By joining these 2, we get the same string back. So this is a very simple concept. It's not complicated. It's very obvious once you think about it, but very few people actually do this. The way people approach regular expressions is through defining just one needle and then trying to just understand it. That's fine if you're an expert, but A, when you're starting, it's extremely difficult to do it like this. And B, if you come back to your own regular expression after like a month or so, you would be very hard put to understand what it means. If you saw the last video like a couple of days back, you might have to spend a couple of minutes to understand what this guy is doing. But on the other hand, if you have the same thing in these 2 portions, you can immediately see that this is looking for the date string and this is looking for the day part, right? So if you execute this, it's exactly the same idea, exactly the same thing, and we get the same result out. But the good thing now is we have a way of modularizing the needle so that we understand it a lot better, right? So let's go ahead and take the more complicated string to drive the point home. So this is our text string. So this is our new haystack, and what we're trying to do is we're trying to figure out this portion over here, the time portion over here. That is what we're interested in. So let's go ahead and break this down. So the first part of our needle is going to be this portion over here up until the space, and the second part is going to be the timestamp over here. So We define strday as 2 digits dash 2 digits dash 4 digits. So that's this portion over here. Then our time is going to be 2 digits colon 2 digits and then a PM, right? And our needle is now going to be the date string, so strday, and then there's going to be a /s, so a space separator, and then the time. So that's our new needle, and we try to find it. So it works fine. However, now we can reason with the fact that if I change this to AM instead of PM, so let's say we go ahead and change this to AM instead of PM, it's not going to be found anymore. That's because we have hard-coded PM into our regular expression over here. Instead, what we want to do is we want to make sure that it can be AM or PM. So the syntax for that is you can go ahead and put brackets over here and you can say AM or PM. So this is a choice. You can have one of these two characters, not both of them, not none of them, one or the other. So let's go ahead and run this. And as you can see, it works now. However, there is another problem. What if this was like capital P, right? So now it's not going to work because these are case sensitive. So we can give it more choice. So it can also be AM in capital or PM. And similarly over here, you can have M as small or M as capital. So if you do that, now you can take care of all of the variations of AM and PM through this guy over here. And from this string, you can see the strength of a regular expression. If you were trying to do this using an if statement, this would be like a jumble of mess of code. But with regular expressions, it's fairly easy to see that we have small a, small p, capital A, capital P, small m, capital M. Everything is a lot more easier to understand. Another thing that you can do is, because we have this guy in a structured form, you can take this str time and you can use it in any other regular expression that is looking for a time. So that makes our life a lot more easier. So there we have it. Now let's go ahead and find that email that we were initially interested in. So this is our haystack again. And what we're trying to do is we're trying to find out this testuser@gmail.com from within it. So let's run this so that our haystack is updated. We have some part over here. So this guy over here is our prefix. Then we have some username at some domain name. And then we have some other stuff over here, which we're not interested in. So we define the prefix as str prefix is equal to .static. So anything can go. Then we have a username over here. Now the rules for username are that they can be small case A to Z. So A dash Z does not mean A or dash or Z. It means any character from A to Z, but in small. Then we can also have capital A to Z. We can also have 0 to 9, and we can have a dot in it. So a dot within the square brackets does not mean anything. It actually does mean the dot character over here. So that's our username. But we can have any number of these. So as before, we can put a static over here, and that means you can have any number of any of these characters. So small a to z, capital A to Z, 0 to 9, and a dot. If you want an underscore, you can also put an underscore over here, but let's leave it at this at the moment. Now, then we have the @ character. Let's forget about that for a minute. And then we have the domain name. So a domain name is anything followed by a dot character. So if I put a dot over here, that's going to mean anything. So I have to escape it in order to make it a dot character explicitly. So anything, then a dot character, then anything, or let's say any number of anything, except we have to make it non-greedy, right? So that's the whole regular expression for our domain name. So what this means is any number of anythings, then a dot character, then any number of anythings, but don't make it greedy, right? So we have our username and we have our domain name. So the email is going to be our username and then an @ symbol and then the domain name. And our needle that we're looking for is some prefix, then a space character, and then our email, and then another space character, right? So we can omit this as well over here, but we're putting it over here so that we can stop at this guy. Otherwise, this dot star is going to match everything up until the end. So we're looking for this specific needle, which is composed of some prefix and then the email, right? So this is the email part and then a space. The email itself is composed of a username and then an @ and then a domain name. So our regular expression is quite modularized, and just by looking at this needle we can understand what we're doing even if we come back to it like a month or so afterwards. So let's go ahead and run this, and hopefully this works. Yes, it does. Everything is working fine. Let's see what our regular expression would have looked like if you were following the general approach towards regular expressions and wrote this in just one big string, right? So let's print the needle out and look at that. This is going to not even look pretty right now, but if you come back to it after a month, it's going to be extremely difficult to understand what you're trying to do over here. And if you made a mistake, if there was a bug, it would be extremely difficult to debug this guy over here. And it's much easier to debug this portion over here because this is now modularized. So make sure you understand number one, the syntax of regular expressions, and number two, the fact that you can modularize it into multiple strings and make it a lot more manageable. This second part is what people typically miss when they're working with regular expressions. So up until now, we've matched the needle to the haystack, but the problem is we're interested only in the email. How do we get this email out of the whole matched pattern? That's going to be in the next video. So in the previous video, we wrote this regular expression which was able to match the string for the email address within a larger string. But what we're interested in right now is to extract the email in a separate string. The whole pattern has been matched, but what we're interested in is just the email address, right? So let's go ahead and do that. So the general idea behind any extraction is whatever you're interested in, simply go ahead and put a parenthesis around it, right? So let's go ahead and put the parenthesis around this portion over here, right? So as you can see, I've only gone ahead and put parenthesis around the username part. So let's go ahead and run this, and you can see that the pattern has been found and rest.group0 is outputting the whole thing. This is where the .group part comes in. .group returns all of the patterns that have been matched. The first pattern is going to be, the 0th one is going to be the whole needle that has been matched, and that is being output over here. Then you can also have rest.group1 or whatever the match variable name was, .group1. So .group1 is going to be the part of the original string that matched anything that was within these parentheses, right? So it's a lot difficult to explain, but a lot easier to demonstrate. So if I say rest.group1, this is going to be test user because this portion was matched as test user in the original string, right? If I go ahead and put the first parenthesis around the domain and run this, then it's going to be this guy over here. I can also do both of them and put parentheses around this guy and this guy, and if I run this, the first one is going to be test user and the second one is going to be gmail.com. We can also go ahead and nest these two. So these two are already staying there. We can also go ahead and put a parenthesis here and another one over here, so they do have to match. So there you go. And now rest.group0 is going to be this guy, the whole needle. .1 is going to be the email address because this is outside, and then within this we can also have more. So 2 is going to be the username and 3 is going to be the domain name. So that's the second strength of making your regular expressions modularized. Instead of going ahead and trying to put parentheses around stuff that you don't really understand or which is very difficult to understand, you have these different variables and you can put parentheses around stuff that you are really interested in because it's much easier to see over here. Let's go ahead and output this needle just to make sure we understand what's going on and what the importance of a modularized regular expression is. So if I print the needle, you will see that it is really weird now. We have parentheses and stuff is just going crazy over here. So it's a lot easier if you do it like this instead of just writing this guy over here, which is typically how regular expressions are explained. So I hope you understood this. Please go ahead and practice with this. Regular expressions are going to be very handy. There are very specific cases in which you need to use regular expressions and nothing else will do. Those are the tasks which are going to be very complicated if you do them with regular expressions, but they're going to be impossible if you don't do regular expressions. So you do have to know regular expressions. Doesn't matter what area of computer science you work in, it's almost a guarantee that you will come across regular expressions and they will save your life.